The broadcast is now starting. All attendees are in listen-only mode.
All right. Well, good morning, everybody. Hopefully everybody can see me and hear me. I'm meteorologist Bob Bright here at the National Weather Service in Charleston. We wanted to thank you all for joining us this morning for our latest IWT. We're going to be focusing today on the tropics and coastal flood. So a lot of water talk today, which I know is certainly a hot topic of late. And first, we wanted to, I'll introduce Blair Holloway. Hopefully you can see both of us right now. Blair is one of our lead meteorologists and coastal flood program leader here. So he'll be running the coastal flood portion, and I'll be running the tropical portion of today's webinar. And we also wanted to introduce for a moment our morning coordination meteorologist, Ron Morales. And he just wanted to open with a few words. Oh, there he is. We can see him now. So Ron, take it away.
Yeah, thanks, Bob. Welcome, everybody. Good morning. I'm really happy to be here this morning. We've got an excellent round of speakers and topics here. You've got Bob and Blair are two of our biggest experts, both in tropical and coastal flooding and hydrology, actually, respectively. And we've also got some really good discussions with some guest speakers that are they're experts in their field. So I think we're really going to have a great conversation. Remember, these meetings are not like a conference per se, where you're just getting everything pushed out to you in one direction. As I remind everybody when we do these, that these are meant to be discussion times. So somebody will give a presentation, and however Bob and Blair have set it up to, if there's time to talk after, they'll let you know. Otherwise, there'll be a discussion time or times during here. Use this time to ask questions, to understand something that you didn't understand before or like to know more about. This is only as good as we all make it with conversation. So make sure it's interactive and ask questions. There are no dumb questions. Let me tell you, these are two very difficult topics for many people, and they are ones that are very, very important to our area and really to anybody along the coast in this country and around the world. So welcome, thank you for attending, and I'll turn it back over to Bob and Blair.
Yep, thank you, Ron. Yeah, we hope to make it somewhat interactive and have time for questions and a little discussion at the end. So just to go over a few logistics, hopefully, there you go. Hopefully you can see that. So just a reminder, we are recording this, or at least trying to, so hopefully we'll have a recording at the end if you miss anything. Everyone, we were going to mute everybody until after each presentation is over, and then we can unmute. We might try to just keep everybody unmuted and ask that you do it just mute yourself on your end. And if that, hopefully that would work a little bit better. So just right now, just try to make sure that you're on mute until you'd like to speak. So we could try to do it that way. If you have any questions or comments, just put them in the go-to panel, control panel anytime, and we'll try to monitor that as we go along. We're going to try a few different poll questions just to knock off some of the cobwebs here in the beginning. So those should pop up, and you can just respond to those. The presenters will be past control, and then you can choose whether or not you'd like to show your cameras at that time. The agenda and the course certificate can be found in the handout section of the control panel. So if you need those, you can download those from there. And like I said, afterwards, we're going to get the copies of the recording and the presentations, hopefully made available to you as soon as we can after the webinar. not today, in the next few days, hopefully. And then there'll be a survey at the end, so hopefully you can respond to us, give us your feedback after that. So just a quick agenda for today. We're going to open up, like I said, with the tropical portion, and then in a few minutes, and then we'll take a little break around 10 a.m. Hopefully be back about 10:10 for the coastal flood portion, and then we'll try to have a little discussion at the end and wrap up around noon or a little bit thereafter. So with that, we're going to jump in. So we're going to start off, hopefully you can see that. Yep. All right, so without further ado, we're going to jump right in here. And I'm going to talk a little bit about the tropical program update for the season. If you've been with us in years past, you know I usually do these webinars just to update everybody on the latest and greatest. This year we wanted to, since there wasn't a whole lot of changes for this season, we wanted to try to take advantage and combine this with the with coastal flood as well. So that's what we're doing this year. Fortunately, there's no significant changes for this season. So like I said, we're going to jump in and pretty much kind of talk about a review of water level products when it comes to the tropical systems. There seems to be some confusion. There's just a lot of different products out there. So we wanted to try to clarify some of that for y'all and talk about that and see if you have any questions about some of those products. And then we'll finish with some key takeaways and reminders. So like I mentioned, as far as the tropical program in general, there's no significant changes regarding products and services for this year. We just do want to mention that the NHC forecast track cone, it looks like it'll be adjusted a little bit for this season, like it is every season. It's not official yet. I haven't seen the official notification, but maybe Robbie can speak to that during his presentation. But it is, like it has been for most of the past several years, since the cone is actually just based on the last 5 years of average track errors from the Hurricane Center, and those have been improving. The cone has actually been shrinking with time. But I think it's going to be about the same size as it was last year. But Robbie can speak to that maybe during his talk if there's any changes to that. And then we did want to mention that the experimental peak storm surge graphic has a new look for the season. So we'll talk about that. All right, so just to review, we thought it would be good to remind everybody and kind of start off with some water level terminology, because there's just a lot of terms out there when it comes to water levels, and it can be quite confusing at times. So hopefully this will break it down for you. And so let's just start off with, and say we have an astronomical tide of around 2 feet. And we measure the tide in terms of a datum. So in this case, on this graphic, it's about a 2-foot tide above mean sea level. Now keep in mind, in this part of the country, our astronomical tides can vary around 6 feet between high and low tides, sometimes even more. So that's why it's quite tricky when we're talking about water levels. You really have to know, where's your starting point, and the starting point is the astronomical tide. So in this case, just for this purpose, say we have a 2-foot astronomical tide. And then here comes a storm, and the storm is pushing water into the coast, and it's bringing an extra 15 feet. So that's technically what we call the storm surge. So we got a 2-foot tide plus a 15-foot storm surge, and that becomes a 17-foot storm tide. Now, when that water pushes on shore, now we have inundation, what we call inundation. So that's the storm surge inundation. And that's essentially the water above ground level, AGL, above ground level. So that's really what our focus is on when we get into a tropical system, is that above ground level. And you can see in the second bullet, you know, water levels can be referenced to different, what we call datum. So above ground, the ground level is a datum, and then we also have other datums, other tidal datums. So that I mentioned mean sea level. But we also have other datums like the mean high water level and the mean low water level. And you're probably more familiar with that mean low water level because that's what we focus on outside of tropical systems. Throughout the year, we're usually focused on the mean low water level. But in tropical, our main focus is on inundation, above ground level, and even that mean high water level, because that mean high water level is essentially a proxy for the amount of inundation. It's not a one-to-one, but it's a lot closer in value than the mean low water or even mean sea level. And then in all of this, just keep in mind in our forecast, we're not including waves. So essentially, the true total water level that gets experienced at every location is not necessarily forecast because we don't have a good way of really accounting for waves on top of the water level. So just keep that in mind. That's not included in the forecast, but certainly waves can add significantly to the total water and the amount of destruction, especially along the beaches. So the main point here, bottom line, you have to know your datum to know exactly what we're talking about. So in terms of storm surge inundation forecast factors, Robbie will probably touch on this a little bit, but there's a lot of different factors that go into forecasting the amount of water at the coast. And we can kind of break it down into the meteorology and then the non-meteorology side. So in terms of meteorology, there's a lot of factors like the storm strength, the size, the speed, the track, the angle approach to the coast. And then again, we have to consider, is the storm paralleling coast or is it going to make landfall? And that's usually a tricky question around this part of the country just because a lot of the storms come up the coast and very close to the coast, and whether they hit land, make landfall, or just brush by, that can ultimately mess with the forecast because that's a very challenging aspect to forecast because sometimes it only takes a few miles difference to affect that. So, and it's also important to keep in mind that the forecast peak inundation values usually don't occur unless the storm does make landfall and are most likely to occur on the right side of where the landfall location is. So essentially, bottom line is that a lot of times, because we focus on more of a worst case scenario with our forecast for planning, a lot of times you're not going to experience the values that we're saying, especially early in the event, because we just don't know all those little details about the storm and exactly where it's going and if it's going to make landfall or not. And then there's other factors. So land elevation, obviously, and topography. You know, the shape of the coastline. You know, is the coast more concave? Is it more convex? So along the Georgia coast, especially being more concave, it's going to keep that water into the coast a lot more easily. So that's something we also have to try to keep in mind. And then also the bathymetry of the ocean floor, ocean off the coast. You know, what is the slope of that ocean floor offshore? Is it steep or is it shallow? So it's shallow off our coast. So essentially the water can pile up and push on shore a lot easier than it can in other parts of the country, especially if we look at down along near Miami, they have a very steep ocean floor as you head offshore. So a lot of that wave energy can essentially be dispersed downward instead of pushing on shore. So it's very highly dependent on a lot of all of these factors, but because this area obviously is the Low Country for a reason, very vulnerable to storm surge inundation. So something we take seriously, and we know that it drives a lot of the emergency management decisions as far as evacuations. So let's backtrack about 30 years or so, go back to Hurricane Hugo. Some of y'all probably remember the storm. Some might not if you're new to the area, but essentially it's our last great big storm in this part of the country. And this is a pretty neat graphic from NOAA Office of Coastal Management, and essentially focus on the middle graph there, which essentially shows the difference in, well, for those who don't know, the storm made landfall as a Category 4 on Sullivan's Island, just north of Charleston Harbor. And that essentially put the highest storm surge inundation up the coast, not in the harbor, but more up into the coast, up toward Avondale, Bulls Bay, that area. And it was around 20 feet of storm tide that was measured up there. So if that storm just 20 miles south, say towards Edisto Beach or so, if that storm had made landfall there, it would have been a completely different story. And the middle part of this graphic shows just all that added water that we would have seen especially in downtown Charleston, 7 to 10 feet more water, and then even 10 to 13 feet more south of the harbor. So it's just a great example of just 20 miles can make a huge difference. So that storm track does matter, and especially whether the storm makes landfall. And also, as bad as Hugo was, and I know, people that have been through it certainly know, I wasn't here, but the stories are pretty unbelievable. It could have been a lot worse, and that's important to keep in mind. So when we talk about our storm surge products, let's kind of just step through. We want to talk about, pre that watch warning phase. So we're talking about more than like 2 days out from the beginning of tropical storm force winds. So we got the forecast cone. Okay, everybody's familiar with this product, or they should be. It can be used for a general, and I underline general, idea of the storm tracking strength. It largely determines, of course, where and how much storm surge will occur. And again, coast paralleling storms are very tricky because small shifts on the track or the wind directions at a time can greatly ultimately impact the amount of inundation. And also important here to remember to not focus on exactly on the cone itself. It's not an impact area cone. It's essentially trying to depict the most likely track of the storm's center only. So just keep that in mind. So a good reminder for everyone about the cone and what it's supposed to represent. So as far as the storm surge products, so before we get into tropical watches, we're coordinating with the Hurricane Center Storm Surge Unit. Okay, they're the experts when it comes to that. The big picture experts for the country. And typically they suggest, we suggest to use a slosh model, meow, or mom product at that point. Now, not everybody has access to this data. If you're in the emergency management community, certainly you all have access to this data via the slosh software program, and then there's also the HURVAC program. And if you're not sure, if you want to try to access that, you can go to those links, those websites there, to see if you're eligible to sign up to get that information. Now, the moms essentially the worst case for each category, but they're usually often way too general and overdone for most locations, so keep that in mind. And the meows are a little more specific, and they're preferred once the storm direction becomes more clear. And there's a new feature in, well, it says HVX. I meant HERVAC. That's essentially the name of it now. But HERVAC meow mixer is preferred since you can combine different storm directions in that instead of in slosh where you can only provide essentially one direction. So you might be able to provide a few directions, combine the output, which may be preferred in some cases. But it's important to remember to use one category higher than the latest NHC forecast near landfall, as well as high tide, especially when you're in that planning mode. Now, another planning tool is the storm surge risk map. Essentially, this is the MOM from the slosh model. The MOM is the maximum of the meow. So for each category, you're going to get a one map that's going to show essentially worst case at any individual location for each category storm. So it'll show you, the areas that are most vulnerable. Not every storm, again, this is just for planning. Not every storm is going to produce that because again, it's highly dependent on a lot of factors. But that essentially shows the worst case for all types of, say Cat 1, Cat 2 storms. And then we also have a neat tool from NOAA as well as Sea Level Rise Viewer. And this is where you can visualize where and how deep the water from storm surge could be at certain water levels above that mean high water tidal datum, which again is a rough proxy for the amount of inundation. So on the left, you can click on select the height of water above mean high water, and then the map will show you what areas and how deep the water could be. And then in some locations, you can click on the a point or for that location and see, say a picture, a landmark, and it'll show a little graphic, an image of how high the water might be at that location. So it gives you a little bit more of a visual about what that amount of water would look like in some places along the coast. So that's a pretty cool tool. Now, once we get into the tropical watch warning phase, so we're less than 2 days before tropical storm force winds, we have a lot more data at our fingertips, and that includes the Hurricane Center's probabilistic storm surge data. And you may have seen this. It's essentially available once we get hurricane and possibly sometimes tropical storm watches somewhere in the U.S. And the data is available within about an hour after each of the main 4 advisory packages, so 5 a.m. p.m. and 11 a.m. and 11 p.m. It's essentially an ensemble of the different slosh model runs using different reasonable scenarios based on the NHC's forecast. And I think Robbie will touch on this a little bit more, but it's better than using essentially probabilistic data. It's better than using a single deterministic forecast just because there's often so much uncertainty, like I mentioned, in the storm features. Now, the data does include the tides, so it factors in the tides, but it's not factoring wind or waves or other fresh water like rainfall. And you can get it in different formats listed there. And it does provide some timing information, so that may help. You can loop through and look at the different times periods, so maybe when you'd be more at risk. And then you can zoom in on the map, but it's pretty coarse resolution. It's not intended to be down to the street level or anything like that. So depending on if you just need a general overview, that's a good resource. And you can also download the data into your own systems like GIS. Now, the potential storm surge flood map is also going to be available once we get into, especially in the tropical watch warning scenario. And the key to keep in mind with this product is that it's always going to represent a reasonable worst case scenario for inundation. So you don't necessarily want to use this a day out when there's a little more certainty. This is always going to be a reasonable worst case 10% exceedance product. So just keep that in mind. It's good farther out in the event to get a good idea. It's more used for planning earlier in the event. And you can zoom in, but again, not down to the street level. And you can download the data as well if you need to. Now, we also have, as of several years ago, we started the storm surge watch warning, and those are issued for broad stretches of coastal areas when 3+ feet of inundation is expected somewhere, not necessarily everywhere in these zones, but somewhere. And the watch warning area is described generically in our text products, but of course it's hard to describe all that detail in text. So there is a graphic available, and that's what we would recommend if you want to get a better idea about what areas are at most risk. And then once we do have storm surge watches and warnings in effect, there is that peak storm surge inundation graphic, and this has been revamped for this season. Nicer look and feel. Again, this will show the peak values along stretches of coast, not necessarily everywhere in those areas, but just gives you an idea. It's essentially the same values you're going to see in the tropical cyclone public advisory from the Hurricane Center. It's just shown graphically, and it's a nicer look and feel for this season. And just wanted to point out, there is a lot of fine print, and especially the title says storm surge, but it's technically a storm surge inundation, so it's representing the amount of water above ground. So just keep that in mind. And then we also have the hurricane threat and impacts graphics, and then of course we got one for storm surge. We also have one for wind, flooding, rain, and tornadoes. But for this purpose, we'll just talk about the storm surge threat graphic. These graphics typically only issued once we locally are under tropical watches and warnings, but we also could be issuing these a little bit sooner than that for regional collaboration purposes as well. And these do incorporate forecast uncertainty, so they're designed to guide everybody's preparations. All right, so before we get into the takeaways, I wanted to do a poll and I forgot. I apologize. So I'm going to launch a poll question here. So just feel free to respond to that. It should pop up on your screens. Hopefully y'all can see that. There you go. So feel free to respond. I wanted to do this ahead of time, but I forgot, so I apologize. So we got emergency management, media, federal, state, local government, academia, or other. So it looks like we got almost everybody voted. So this just gives us a good idea about what type of folks are on. So we'll close that. And it looks like, you can share that. So it looks like we had most everybody is emergency management. We also have some media, some academia, and also quite a few government. So, all right. So we'll hide that one. All right, so we'll keep going. I do have another poll question or two, but we'll talk about that in a second. So again, the key takeaways here, our focus, from the Weather Service aspect is, of course, on the protection of life and property. So we just want to remind everyone that we're, pretty much always going to err on the side of caution when it comes to the forecast. And we're going to lean toward that reasonable worst case scenario for planning purposes, especially early in the event. And it's imperative to understand the purpose of each product and when best to use it. So if you're ever in question about a product, please don't hesitate to ask us if you're confused. And during tropical systems, our focus is on providing water level forecast relative to ground level or inundation, not relative to tidal datum. So, again, that's important to keep in mind because it is a little change in our philosophy from the way we normally operate, outside of tropical systems. So, and that mean high water tidal datum is the best proxy. If you're going to reference a tidal datum, that's the best proxy for ground level. So sometimes you'll see that we will try, if we talk about the water levels at our tide stations and things, we'll try to at least also reference that mean high water level, focus more on that as opposed to the mean low water level. And of course, in tropical events, messaging is really important. We just want to remind everyone to focus on the dangers of each hazard, especially water. Water is, essentially the biggest killer when it comes to tropical systems. So focusing on the dangers of the hazards, also communicating the impacts of those hazards, focusing on the official NEC forecast as well, and only, sharing and utilizing reliable sources like the Hurricane Center. And then also after the storm passes, highlight the hazards that continue. And a lot of times, we're still going to be dealing with flood, water issues. So certainly after the storm, we could be dealing with continuing hazards. All right, so I wanted to quickly show our tropical page and just remind everyone just from our main webpage /tropical, and pretty much is a one-stop shop for all of the tropical information. At the top, you can get our latest briefing if we have any issue, as well as our hurricane guide, which is designed for the public just to provide. It's a good resource for, what the different products are, how to use them, and a lot of preparedness information. So we encourage you to use that, even before the season, before the storms, and try to share that out with the public. But essentially, you can get all the information on all the different products, like I mentioned. But one of the cool things is the threat and impacts tab. So I just wanted to show that real briefly. You can click on your location, and then up will pop the 4 different threat graphics, like I mentioned. And so it'll give you the threat levels, what areas are under the different threats, and also you can get the potential impacts from the different threats and what people essentially should be prepared for. And then also it'll also display essentially from our TCV product, which is county or sub-county based, you can get more details about what headlines are in effect, locations in those counties or zones, and then the different aspects of the different hazards, what to expect, what you should be preparing for, that type of information. So it's really a nice kind of compilation of the different products in one little way there on that website. So we definitely suggest you utilize that. And then, we're always looking for feedback. So this is something that the National Tropical Program is wanting some feedback on. So, obviously we're talking about more about the surge water level products, but if you have any feedback regarding our wind speed probabilities products, whether it be the graphic or the text, how you utilize those, when, during an event, which thresholds you might use, feel free I did add a question in the survey after the webinar is over, so you can provide any feedback there, or feel free to email me by around May 25th if you have any feedback to provide us. And then I wanted to wrap up with the hurricane season outlook. And essentially, it's blank for a reason. We really don't want everybody focusing on the outlook, to be honest. So yeah, officially, that's our main takeaway. It only takes one. Prepare the same every year. But if you want to know the outlook from NOAA, it'll be coming out in a few weeks. But there are early indications are that it looks like it will be, another above normal season. But again, like we've seen in past years, it doesn't necessarily say whether we're going to be impacted. So we definitely encourage everyone to prepare the same every year. All right, so we're going to launch another poll. Should pop up. See if everybody was paying attention. So feel free to answer that. See if we caught anybody off guard. I was going to do this ahead of time, but it still works after the fact just to see who was paying attention. All right, so we got about 60%. So we'll go ahead and close the poll and then share the results. See how that turned out. And as you can see, most of you were paying attention, but there are a few other answers: mean low water, mean sea level, and NGVD. And so, yep, the correct answer, most of you all had it right. Mean high water is the proxy for the amount of inundation. So again, don't focus on mean low water. I know we focus on that pretty much for all other types of storms throughout the year, but during tropical events, our focus is on an inundation above ground, and the best tidal datum, the best proxy is mean high water. So you're going to see quite different values if you're looking at the mean low water. You're going to see a lot higher values if you're looking at that datum. So be sure you're looking at least at the mean high water datum, especially inundation. All right. So we're going to try one more poll here. This is just more for fun. So since 1950, we had two. There you go, it should be open. We had two major hurricanes made landfall in our forecast area that runs from Charleston County all the way down to McIntosh County. So which phase of ENSO do you think those occurred in? So the two hurricanes being Hugo and Gracie. It looks like we had a split, pretty much even there between ENSO or El Nino, La Nina, and neutral. And I believe everybody got the right, or most people got the right answer, neutral. So typically we will we usually see more neutral phases in general. But it is, and we typically do see more storms in this area affect us generally during La Nina. El Nino is generally less favorable for most hurricanes and tropical systems in the Atlantic. Although it is interesting, when we did our little climatology product a few years ago, we did find early in the season, it doesn't really matter too much. Typically the storms, we actually have seen slightly more storms during El Nino early in the season. But really, when we get later in the season, when we typically see our bigger, stronger storms, those are more favored during La Nina. So a little climatology there, just to make it a little more interactive. So right now, I will hide this poll, and that wraps up my portion. I will, if anybody has any questions, everybody should be unmuted if you have a question. Feel free to ask it now.
I have a question. I can't turn my camera on though. This is Mary.
Oh, hey, Mary. Yeah, go ahead.
Yeah, so as we are in the high school classes that we're working with, trying to basically build some interactive storm surge modeling with graphs and actual waveforms, we were specifically trying to decide what standard to use as the bottom of, say, the wave. And that idea of not counting the top of the wave is really interesting. So why is it not as effective to, say, use an elevation data that you can get from GIS versus mean high water? So if your home's elevation can be found on GIS, and then you can say, all right, there's a storm surge that's predicted to be 6 feet above. So if you're saying 6 feet above mean high water, how does that compare to, say, a ground elevation on GIS? Is it significant? Is it statistically significant, or should we just, you want us to start using mean high water for everything?
I guess I'm a little confused about the question. I don't know. Does anybody have a, Robbie or Blair maybe? Does anybody have an idea?
Hey, I'm here too, Bob. This is Doug Marcy. I can.
Oh, hey, Doug. Yeah.
Yeah, hey, Doug.
Thanks.
Or Robbie. Robbie, I see you talk. You guys do datums all the time, so maybe you could take that one.
Yeah, I mean, I'll just briefly say that the modeling that's done at the Storm Surge Unit and Weather Service is done off of what's called the geodetic datum, so NGVD 29,
Right.
for example.
Right.
But, and that's the more accurate, most accurate way to do modeling. But what we're doing is the communication side of it. Nobody knows what NGVD 29 is.
Oh, okay.
For most advanced users. So what we do, and I'll get into this in the next talk, is that we convert everything to inundation, which is above ground level, because that is what the public understands. If they're standing on land, how high is the water going to be where they're standing? The mean high water that Bob was talking about, we only use that when we're looking at tide gauges during an event or in the post-analysis after an event, because we don't have real-time measurements of how high the surge is getting when a hurricane is making landfall.
Right.
So we're using the mean high water datum as a proxy for the highest inundation that's likely occurring near that tide gauge. So those are very distinct differentiations between geodetic and mean high water and inundation above ground that we have to keep distinct, whether it's the modeling side of things, the observing side of things, or the communication side of things.
And do you mind if I ask one more question? Because the kids are asking this too. So if you've got with greater and greater wind speed, you're going to be piling up more water. At what point do you start to talk about, say, the potential height of a wave on top of the surge? If they're living in, say, a public housing project whose highest floor is 12 feet off the ground.
Yeah, I mean, the coupling of waves with storm surge models is still, and it's still being advanced. Let's put it that way. And so, in the storm surge unit here, the Hurricane Center is working on some new models that do incorporate waves But mostly that's for island locations like Puerto Rico, the Virgin Islands, because
Right.
those environments tends to be more significant. We haven't yet got to the point where we're coupling those waves in a probabilistic sense for other parts of the United States. Not that it's not a contributor as far as how high the water might get, but it's just not something that's been coupled to the point where we can use it operationally.
Okay. All right. Thank you so much.
Yeah, this is Ron. I just wanted to go along with what Robbie was saying and double down on it, I guess, is that even though the waves aren't incorporated specifically yet in the modeling, they are significant, or they can be significant, particularly for shore facing, directly facing, say, the ocean. So, Isle of Palms versus the backside of a barrier island or up in the harbor is going to be very different for wave action. So it would be very, very difficult to get an accurate forecast, and never mind measurement too. I mean, we have difficulty measuring wave heights, even on everyday forecasting when we're doing surf forecasting and trying to get a beach patrol or not Coast Guard, beach patrol or lifeguard to give us surf heights. Just measuring that, if you don't have a very deterministic way to do that, say with some sort of instrument, that's going to be subjective in itself. But waves, once you get deep enough water, now you're going to say, well, how deep? Deep enough to generate some sort of wave, several feet, you have to have a depth of water to generate a wave. And once you do, then those waves can now act as being more damaging or potentially allow water to lap up or reach into areas that the steady or still the stagnant water level wouldn't have reached. We know that it exists, and all you can do is tell people that that exists and that potential is there. So it would actually be worse or potentially worse than just what the static water level might rise to, if that makes sense.
That's very, very helpful. Thanks, Ron.
Okay, anything else real quick before we jump into Robbie's?
Hey, I have a question.
Yeah, go ahead.
Hey, this is David Green in Colleton, and I know I wasn't around in '59 when Gracie hit, but I understand that could have been a lot worse if it was high tide when Gracie hit, and I'm trying to get my head wrapped around Gracie moving through in 6 hours and it not being high tide. But where positionally would the storm be in relation to the tide that would be of most concern? Would it be making landfall during high tide, or would it still be off the coast at high tide? That's kind of a question.
Right. Yeah. So definitely, like I mentioned, you have to know what part of that astronomical tide cycle you're at. So if you're at, low tide, like I said, those tides can vary like 6 feet or so. So that's essentially, if it happens at peak high tide, you get your peak storm surge at the same time as peak high tide, you're essentially adding a whole lot more water on to the event than you would if you were at low tide. So, trying to forecast exactly when all that's going to happen and where, and the wind directions and all that's what makes it very complicated as far as determining the ultimate amount of storm surge inundation at every single location across the coast. Does that answer?
So I guess, yeah, and in my mind, this is what I'm thinking. You tell me whether I'm right or not. The worst case scenario would be an approach when we're leaving low tide on the way to high tide as it approaches the coast. So then you kind of maybe have almost 12 hours, right? So you're going from low tide to high tide, and the closer it's getting, the closer we're getting to high tide, and then it's very near the coast then once we hit high tide. That would be the worst case scenario. Is that accurate then?
Yeah, I don't know, Rob, if you have anything to add to that, but I think what happens a lot of times is as the storm is approaching, you do build up water ahead of the storm. And so even if, you have a low tide, that low tide is going to be not as low as it normally would be, just because you have a lot of wave energy and wind pushing, you're already essentially starting to get storm surge ahead of the storm a lot of times. So you'll that low tide won't be as low as it normally would be. And then once you get, if the storm comes in exactly at peak high tide, then essentially your worst case scenario. But again, not every high tide is exactly the same water level. So, that matters too. I mean, we're trying to incorporate all that into the forecast, but does that help?
I'll add to that real quick. I just happened to have the page up, so I pulled up the data from Gracie from September 29th, 1959, and the peak tide level coincided almost exactly with low tide. And so at low tide, comparing it, this is data from the Charleston tide gauge, the peak tide value was 8.14 feet, and that was at low tide. So the surge that we experienced was nearly 8 feet. And so if you take that value and you just have it perfectly coincide with the high tide on maybe a little bit later, the next high tide was predicted to be just over 6 feet. So it had that been kind of the perfect timing of the peak surge occurring coincident with the high tide, you could have conceivably had a peak observed tide value that would have been somewhere around 14 feet, which would have been higher, more than, I guess, 1.5 feet higher than what we observed in Hugo. So it's the worst case, obviously, I think like Bob was saying, was that you want the peak surge coinciding with the high tide. That would kind of create the worst case scenario.
I got you. Thank you.
Okay. All right, so we'll move on in the essence of time here. So Robbie, you want to go ahead, and looks like we can see your screen. So
Sure.
All right. So
Hey.
This is Robbie Berg from the National Hurricane Center. Sorry about that. Now senior hurricane specialist. So congrats on that, and we're glad to have him here joining us. So if you have any questions for the Hurricane Center, save them up, and you can attack them later at the end. So go ahead, Robbie.
Okay, yeah, thanks, Bob. So, Bob touched on a lot of the products that we issue at the Hurricane Center for storm surge, and I'll go a little bit more in depth on some of them and how they're created and how we should be interpreting them during a hurricane. And I really want to frame much of my talk around understanding risk, because when it comes to high impact events like a storm surge event from a hurricane, we can't rely on just one, what we call deterministic forecast, which is just one run of the storm, modeling the storm surge and making essentially what we think is going to happen, because that can get you into trouble. So what I want to do first is show you an example from last year. This is actually Hurricane Ida, which hit southeastern Louisiana as a Category 4 hurricane. On the left side of your screen is an image of Ida's track there in the black, making landfall near Port Fourchon, Louisiana, and then moving up just to the west of Lake Pontchartrain, and then farther north into Mississippi. And that's a very crude simulation there of essentially the storm surge that occurred with Ida. But one of the questions we always ask ourselves after storms is, well, what if the storm shifted just a little bit? What if its characteristics changed a little bit? And Bob kind of showed this with the Hurricane Hugo example. So in the case of Ida, we said, okay, well, what if we shifted the track of Ida just 15 miles to the east? And on the right side of your screen, you can see in the bold green line is Ida's actual track, and the dashed green line is the hypothetical or alternative track that we kind of wanted to see what would happen had Ida essentially moved a little bit closer to the city of New Orleans. And we're not talking by a lot. 15 miles is all we're talking about here. One thing I should couch here is that 15 miles is well within our 24-hour forecast track errors. Right now, based on the last 5 years, our 24-hour track forecasts are averaging about 30 to 35 nautical mile error. So if we're talking about a shift of 15 miles only a day out from landfall, that's well within the normal errors. That's well within the normal wiggles and slight shifts of a track that we might see with these hurricanes. So on the left figure here now, what you're seeing is Ida's actual track. We took that track, we took the parameters of the storm, ran it through SLOSH, which is the Hurricane Center, the Weather Service's storm surge model. And you can see there on the left is the flooding footprint that occurred with that actual track. So we have our colors from blue all the way up to red, with red areas meaning greater than 9 feet above ground level. So that's above all of our heads because we're all less than 9 feet tall. What you notice in the New Orleans area is that they have many levied areas. And you can see that by the kind of the hatched, cross-hatched areas. There are some that are in black, there are some that are in purple. The purple ones are indicative of being overtopped. In other words, the water got so high that it overtopped the walls of those levied protected areas, and water started flowing into them. So based on Ida's actual track on the left, we had some of these levied areas, including the LaRose, Golden Meadow levee, and so a few others there to the east along the Mississippi River that were inundated or had some inundation due to Ida's track in the storm surge. Now, on the right, what you're looking at is that 15-mile shift to the east. So now we're talking about to the east, just to the east of that LaRose Golden Meadow levee, and then a little bit closer to the city of New Orleans. And you'll notice that the flooding footprint of that alternative track is different. We have a lot more reds in the area. We have a lot more reds up against that levee that's on the southern side of New Orleans. That's actually the city of New Orleans that did not get overtopped, that levee in Ida, but had the track of Ida shifted just a little bit to the east, 15 miles, now we would have seen some overtopping into the southern side of the city itself. So you can imagine if you're an emergency manager in the city of New Orleans, and we're talking a 15-mile difference is that critical, how do you plan for that? And that's where the risk really comes in. If we were to take a difference between those two images, what you're seeing here is the alternative track minus the actual track. And you'll notice that there are some cases here against that levee system where storm surge heights would have been 5 to 7 feet higher along the New Orleans West Bank levee had Ida tracked approximately 15 miles to the east. That's significant. Remember, 24-hour error, as I already mentioned, is only about 30 to 35 miles. So a 15-mile shift to the east is well within those errors. And that's still something we have to account for even 24 hours before landfall. It's not just the track. This is closer to where you all live. This is Hurricane Florence up in the coast of North Carolina. On the right is what actually happened with Florence. So you can see the storm came up to the northwest with that black line, and it turned to the west, making landfall near Wilmington. Most of the storm surge occurred to the north in the Pamlico Sound area. So places like New Bern got heavily inundated by as much as 9 feet of water because of Ida's track, its size, and so forth. But look at the left side. The left side is that if you assume the same track of Florence, but the storm was stronger and smaller. So recall that Florence made landfall in North Carolina as a Category 1 hurricane, and yet it still produced a 9-foot surge in New Bern. Had it come in at a stronger category, but at a smaller size, we still could have seen those values, but look how the displacement or the shift of where that maximum surge would have occurred. It's no longer in Pamlico Sound in the New Bern area, but now it's down the coast in areas like Jacksonville, North Carolina, and so forth. So we talk about the track being sensitive, but it's also these other parameters, the intensity of the storm and the size of the storm. They also make a big contribution. And again, those are parameters that even 24 hours before landfall, we may not still know certain enough to give you a pure deterministic forecast for the storm surge. We still have to account for the risk. So as Bob mentioned, there's many parameters that actually dictate how much storm surge may occur. It's the hurricane's track, its intensity, its size, how fast it's moving kind of in a forward sense. So is it a slow creeping storm or is it a very fast moving storm? And then the local coastal geography and bathymetry also play a part. So because there's so many factors that play into this forecast, and even 1, 2, up to 5 days beforehand, we don't know how each of those parameters will end up. We have to use probabilities to appropriately assess our risk. So that leads us to the kind of the modeling side of what we're using at the Hurricane Center and within the Weather Service. And that's this probabilistic storm surge model that we use for hurricane events. Excuse me. So what is P-surge? Well, here's an example of a storm. This happened to be Hurricane Irma. And if you don't remember exactly, Irma kind of grazed the north coast of Cuba, and then it made a turn to the north-northwest, moving across the middle Florida Keys, and then very near the west side of the coast of Florida. So what P-Search does is it says, okay, well, that might be the forecast, but we're going to add alternative tracks, alternative sizes, alternative forward speeds, alternative intensities. All of those parameters that play into storm surge, we're going to alter them just a little bit. So what you're seeing on your screen is all of the alternative tracks that P-Surge used for that particular forecast. So you can see now we're accounting for possible tracks as far east as the east coast of Florida and as far west as just offshore, with landfall occurring up closer to the Apalachicola area in the Panhandle. So that's kind of the realistic universe, let's say, of alternative tracks that could have occurred with Ida. And again, we're also altering the size of the storm, the intensity of the storm, and how fast it's moving. So P-Surge is just a statistical dynamical forecast system, which uses, again, SLOSH. That acronym is Sea, Lake, and Overland Surge from Hurricane model. It's based on the official NHC forecast and 5-year errors in that official forecast. So we take whatever we know, let's say we're in 2022, we look at our errors from 2017 to 2021 to use that as a guide for how wide that swath of alternative scenarios should be. Again, I won't harp on this too much, but it still includes all these factors that we talked about: cross-track uncertainty, along-track uncertainty, intensity, and storm size. Now, some people might say, well, how do we know that those are realistic? Well, here's an example of another storm, Hurricane Michael, which made landfall along the coast of the Florida Panhandle. And what I'm showing you here is ensembles from the GFS model. So the GFS model is the American model. Most of us are aware of the GFS as it provides a one-track forecast for what's going on or what to expect. But most of the global models we deal with have ensembles themselves. So it's not just one track, but actually a spread of possible tracks or possible scenarios of how the weather might pan out. And so this happened to be the tracks from the GFS ensemble for that particular forecast. And you can see that everything was pretty tightly clustered and making a potential landfall somewhere along the Florida Panhandle. Well, we can look at the European model, same thing, another highly accurate global model. It also has its family of ensemble members, and that's what it happened to be showing at the same time. So what you can tell is that here are the P-Surge realizations that we used based on our 5-year errors, and it actually aligns pretty well in this case with the ensembles from global models. So these ensembles are fairly representative of the types of scenarios that we might see, and they do account for these other possible tracks that are well within the realm of possibilities. So in this case, you can see for Michael, we're using those P-Surge ensembles. We take what's called the 10% exceedance, which is what we consider a reasonable worst case scenario at each of these individual locations along the coast. And this is what we tell people you should be preparing for. Because we don't know exactly which of these tracks is going to pan out, you have to prepare for the one that might be the worst. And that's what this product is meant to show you. So that's where we go from taking the modeling of surge through the probabilistic framework to inundation. And we use that or show that on the potential storm surge flooding map. So many years ago, when we were developing this map, and I think we had this conversation just a few minutes ago, when we're communicating to the public, people don't know what NGVD29 is, or MHHW, or MLLW. It's just these datums are foreign to most people. Yes, decision makers might know what they are. Yes, we meteorologists know what they are. But for most of the people we're communicating to and with, they don't know what these datums mean. So this is a study done by Jay Baker at Florida State University, where he actually polled people in the state of Florida, and he asked them to correctly assess their estimated elevation of their house. And he gave them a 5-foot interval. They didn't have to get it exact. He just said, within a 5-foot interval, tell me what the elevation of your house is. And then he was able to geolocate their house with elevation data to see if they were accurate or not. And what you can see on this circle graph here is that, first off, more than half of people didn't even venture a guess. They just had absolutely no idea what the elevation of their house was. Another 19% were too high, another 12% were too low, and only 14% of the people that were surveyed were able to accurately assess their elevation within a 5-foot interval. So, this data clearly shows us that people, on the whole, don't know their elevation. So if we give them a storm surge forecast above, let's say, 8 feet mean sea level, and they don't know how high above mean sea level they are, that forecast is essentially useless to them. So what we've done is we've moved to this inundation framework. On the bottom is the old way, is using mean sea level. So we would model and simulate surge, and you get, here's the surge line with the height of the water, and it's 5 feet above mean sea level. And you can see that at each location, it doesn't matter where you are, it's 5 feet, because we're measuring it against that data, mean sea level. But what if you're well inland? What does that mean to you? Again, if you don't know that your house, which might be sitting right here, is say 4 feet above mean sea level, then you can't do that 5 minus 4 subtraction to get 1 foot of inundation. So what we've actually done is we've taken the guesswork out of it. We know what the elevation of the ground is based on LIDAR and other high resolution data, and we can take the surge forecast above the datum, say mean sea level or any other datum, and subtract what the ground elevation is above that datum to get the difference. And that is what we consider inundation. So for example, right at the shoreline is where you would expect your maximum inundation, in this case, 5 feet above ground. But as you move inland, as the ground slopes up and you gain elevation, now that same surge is maybe only producing a 1 foot inundation above ground level. So we have already done the conversion for people so that they don't have to know what their elevation is. This is what it looks like. This is the P-surge guidance using the 10% exceedance, reasonable worst case scenario, not very pretty, but when we subtract out the land, now you can see that there's a pattern that develops based on the land elevation. So the lower lying areas have a higher inundation, and as you go inland, as ground slopes up, then we have lower inundation until you get to the point where the water is not able to penetrate any further inland. So that's how that product works. Here's the rundown. The potential storm surge flooding map, we say is that it provides a quantitative risk assessment for decision makers, and it essentially tells you what you should prepare for. Again, because it's accounting for the uncertainties. It's taking all those alternative tracks and simulating storm surge. Excuse me, it's telling you what you should prepare for given that uncertainty. The product shows the height above ground that the water could reach at each location. And this is really important. It's not a flooding footprint. Because it's many storms, it's a composite of many storms, it is not a flooding footprint in itself. It's just a risk map of what areas could get flooded and how high the water could get if things match up just right. The map does include tide, so you don't have to worry about that conversation because we're able to model the storm simulations, and based on those simulations, at what point is it near the coast at which part of the tidal cycle. So we're already including the tidal cycle in the modeling. It depicts the reasonable worst case scenario at any individual location and shows the inundation levels that have a 10% or 1 in 10 chance of being exceeded. So we're not at the highest possible values, but we're kind of in that upper range of, again, what we call the reasonable worst case scenario. This is a little bit new and many people may not have realized it, but the first map can now actually be issued 60 hours prior to the onset of tropical storm force winds. Typically, this was only issued 48 hours before those winds would arrive when we got to the watch time frame. But the Storm Surge Unit has able to advance the P-surge model enough that we've pushed it to 60 hours. And at the end of the talk, I'll talk about where we're going even after this. So this is some great advancements, being able to push this guidance out farther in time, because we know decision makers have very key, important decisions to make days before a storm hits, such as evacuation decisions. And I think, as Bob mentioned, this product is available about 60 to 90 minutes following the release of the actual advisory. Here's a nice schematic showing what the graphic shows you. So if you're in that red area, it's essentially possible greater than 9 feet above ground level. And then on the right side, you see Weather Service Communications has developed this graphic, which shows, based on a family in their house, what does that actually mean? So the red would be above everybody's heads, and the water could be reaching up to the roof, all the way down to the blue, which is a 1 to 3 feet above ground, which means obviously, still up to people's legs and getting a few feet of water in the house itself. So we like to use that for our communications. Now, as I said, this is based on probabilistic data. And when we're making probability forecasts, it's not as easy as, say, me verifying my high temperature forecast tomorrow. If I forecast 80 degrees tomorrow and it gets to 78 degrees tomorrow, then I know I was off by 2 degrees. But when it comes to probabilistic data, it's not a deterministic forecast where we're saying this is what's going to happen. We're giving you a range of possibilities. And the way that we essentially verify a probabilistic forecast is what's called reliability diagrams. How reliable is the forecast? If I tell you that there's a 40% chance of hurricane force winds, then we would expect hurricane force winds 40% of the time that the scenario presents itself to us. That would mean we are making a reliable forecast. So what you're seeing here on this graph is balancing the probability of detection, so the probability that we can say something's going to happen, versus on the bottom the false alarm rate, which is that we make the forecast, say it's going to happen, and then it doesn't. And this is where the probabilities come in. So on this graph, what you really want to be is up in this upper left corner. That means a perfect forecast, because at that point, your probability of detection is 100%. In other words, we're nailing every event that occurs, and our false alarm rate is 0. In other words, we're not overwarning, we're not crying wolf. So we really want to be as far up to the upper left part of this diagram as possible. What you notice with these red and blue lines is that each one of these is a different exceedance. So we have our 10.1 would be 10% exceedance, 0.2 would be 20% exceedance, and so forth, all the way down to 0.8 and 1 down here on the lower left. The two colors are the versions of P-Surge. 2019 was the current version at the time. 2020, we had an advancement of the model, and it's the new version. So you can see that that model has shifted closer to the upper left corner, which means that new P-Surge is more reliable than the old version. What I also want you to notice is why do we use 10% exceedance? Well, you'll notice here that look where the 10% and even maybe the 20% lie. They're relatively high on probability of detection. And even though the false alarm rate is up there, it's still less than the 50% false alarm rate. So with these high impact events like a storm surge event, we feel it's most pertinent to have a high probability of detection. We don't want an 8-foot storm surge event to occur and we not tell you about it. We want to be able to detect that. So we are willing to accept a probability of detection of, say, 80% with the 10% exceedance with a false alarm rate of, say, 40 to 50%. Whereas if we had used a lower exceedance, say a 50% exceedance, look how that false alarm rate goes down, but look how the probability of detection also goes down. So this is all a balance. When you're using probabilistic data, you can't nail it all the time, but you have to find that balance between not crying wolf, but being able to capture those significant events. So how do these exceedances differ? And then why is it important we use 10%? Well, this is the case from Hurricane Florence. You can see Florence there on the right. The forecast was for it to make landfall. North Carolina is a major hurricane. This is when the hurricane watch first went up. And on the left side is the 10% exceedance, storm surge flooding from Florence. On the right side, or in the middle, is the 50% exceedance, which is like a most likely scenario if you want to think about it that way. Notice how different they are. And again, this is only about 2.5 days before landfall. So keep these images in mind, because this is what actually happened with Florence. On the left side is the assessment or the simulation of what happened with Florence. Once we knew all the parameters, once the storm made landfall, we knew exactly what it did. Look what happened in the New Bern area. So we had areas that had at least 9 feet of inundation. On the right side, again, is the potential storm surge flooding map that uses that 10% exceedance. And you can see that, in fact, that product was able to capture those high storm surge values in the New Bern area. Now, yes, there are some areas that got way more, or way less, I should say, than what was shown in that map as you go further east of New Bern. But let me go back again. If we had used the 50% exceedance, there's just a speckling of blue in there. So that's not a very effective warning tool or communication tool when we're trying to tell people how bad it could get during a storm. So that is why we don't use the 50% exceedance. Its probability of detection, especially 2 days away from landfall, is just way too low for us to use it as an effective communication tool. Okay, so now let's move on to the experimental peak storm surge forecast. Bob showed you an example of this. I think he showed you the one on the right. We also have this example on the left. This would have been an experimental product from Hurricane Laura, which hit New Orleans 2 years ago. I'm sorry, Louisiana 2 years ago. And you can see this one happens to have a little bit more colors because the storm surge was a lot worse, with that magenta color being 12 feet or more. So what we're intending to do with this product is to, in a high level sense, kind of show what are the peak storm surge values that could occur along different areas of the coast. And this product is not new in a sense in that the values you see on this graph are exactly the same as the values you would have seen in the public advisory issued by the Hurricane Center. So all we're doing is taking the text product and transferring it to a graphical product. What this product is showing you is a forecast of the peak storm surge inundation expected to occur somewhere within the outlined area. Notice how I emphasize that word somewhere. It's not everywhere in the area. Again, because we know there's uncertainties in the forecast of where the storm actually makes landfall. But for example, between Johnson Bayou and Rockefeller Wildlife Refuge, in this case, somewhere within that area, we expected 15 to 20 feet, as high as that amount of inundation. So this product is meant to be a high-level look at expected storm surge inundation. It is introduced when a watch or warning is in effect. It's the same as the values in the NHC public advisory. And I think the last point here is really important, is that this may differ from the potential storm surge flooding map, since that previous map that I showed you depicts a location-specific reasonable worst-case scenario. This product takes that probabilistic data, but also the forecaster's skill and intuition to come up with a product that shows you what the peak surge inundation values may be between different points. So they do have slightly different purposes. The previous one is location specific. This one is more of an aerial look of what the storm surge may be. And lastly, I just want to touch on the storm surge watch and warning. These were introduced a few years ago. There are the definitions and calls to action. I won't read through them fully, but I'll just say that the warning means that there's a danger of life-threatening inundation somewhere within the next 36 hours. And the storm surge watch is that there's a possibility of life-threatening inundation somewhere within the next 48 hours. So here's an example of a storm surge watch warning graphic. The top point here, this is what I want you to take away from this entire talk, is that the watch and the warning are not a forecast, but they're a risk communication tool. In other words, when we put up a storm surge warning, we're not explicitly saying that we think everybody within that warning is going to get at least, say, 3 feet of inundation. But we're saying because of the uncertainty in the forecast, everyone in that area should be prepared for 3 feet of inundation. So it's a risk communication tool, not an explicit forecast. The product is intended to enhance public response to instructions from local officials. Again, it highlights areas that have a significant risk of life-threatening inundation from storm surge. The product, essentially the watch, is issued 48 hours before the possibility of life-threatening surge or other hazards that would hinder evacuations. So oftentimes with the storm surge watch and warning, the issuance of that is tied to when we think the winds are going to arrive on the coast, because once that time comes, evacuations can no longer occur. So in most cases, the storm surge watch and warning is tied to the hurricane or tropical storm watch or warning because it's based on the wind. But there are some rare cases where maybe the surge would precede the wind and we can issue the storm surge watch and warning separately. And it's important to note that this watch and warning is a collaboration between the Hurricane Center's hurricane specialists, storm surge specialists, and the local National Weather Service WFOs, such as the one in Charleston. So that's a lot of information. Just a quick touch on what's coming soon. First off is that Storm Surge Unit, the Weather Service, is looking at moving to what we call polygon-based warnings in lieu of grid-based warnings for the Storm Surge Watch and Warning. Example there would be on the upper right is more the grid-based, and then the lower right is more of the polygon-based. You can see that what this ends up doing is it gives us more precise warning areas, and it actually reduces overwarning because we're able to more intricately get in, but where we think that storm surge may reach warning criteria. So that's still being worked on, and we're hoping in the next few years we'll get to that point. And As I already mentioned, that the P-surge guidance has been extended to 60 hours before the onset of tropical storm force winds. So that's beyond the watch time frame. But expected next year in 2023, the storm surge unit thinks that we're going to get to a point where we can extend it even further to 72 hours or 3 days prior to onset. And why do we think that? Well, now what you see is, again, those kind of rock diagrams, as I showed earlier, where we want to be as far to the upper left as possible. The one on the left is essentially, I'll just say it's the 2.7 version of P-surge. It was one from several years ago. And one way that we can calculate the skill of P-surge is by looking at essentially what's called area under the curve. And in this particular case, the 48-hour forecast area under the curve was 0.73. That would be that blue line there if I looked at the area under that blue line. The diagram on the right is the updated P-surge with the new advancements. And now if I look at, let's go beyond 48 hours. Let's go to 60 and 72 hours, which would be the green and gray curves. Look at the area under the curve. Those are 0.75 and 0.7. So essentially what we're seeing is that the model has been advanced to the point where our skill at 60 and 72 hours is just as good as the skills we had for 48 hours just a few years ago. So I think that what this shows is that we're now getting comfortable in being able to provide this guidance out further in time because we're not losing skill at those longer lead times. And I think this is great because once we get comfortable with this, once P-surge does get extended, that means we can also extend the potential storm surge flooding map. And that'll give decision makers more time to use that product when they're actually making those evacuation decisions and other key decisions before a storm. So I think that's some exciting stuff to come. I know I covered a lot in this talk, but I can stay on for a little bit to take some questions. I do have to run at some point to the Florida Governor's Conference where I am in West Palm Beach. But I was really happy to be here with you guys and appreciate Bob extending the invitation for me to talk to you.
Yeah, thanks, Rob. I appreciate that. I just wanted to make one quick point. I know a lot of times we just talk about storm surge, and like I tried to explain before, there's a technical definition of storm surge, just that added water above the astronomical tide. But a lot of times you'll hear, you know, like Robbie was talking about, just storm surge. But what we really mean most of the time is that storm surge inundation, so that water above the ground level. So just to make that, you know, as clear as we can, remind everybody, especially when we're talking about tropical systems, that is what we're talking about. So does anybody have any questions for Robbie, since he'll probably have to jump off here soon?
Bob, this is Ron. I have one quick question for Robbie.
Yeah, Ron.
Robbie, first of all, excellent presentation. Thanks so much for taking the time to do it. Just for my own understanding, back on the peak storm surge graphic, the experimental one, is that actually the 50%, like the most, we use the words expected, or so is that actually statistically the 50%, or are we just sort of doing a subjective analysis of the 10% exceedance one?
So yeah, this is where it's tricky again, because you remember the difference between this and the other graphic is that the potential storm surge flooding map is point specific data. This one is not. What the forecaster is doing is they're using P-surge as guidance, but they're actually looking and integrating, in a sense, across segments of the coastline to come up with a forecast of what they think is the maximum surge that may occur within a segment. So it's not a 50% exceedance. It's not even a 10% exceedance because it's aerial coverage, not point-specific coverage.
Excellent. That's good to know. I think I misunderstood that from the training I had taken a while back. So I just wanted to clarify that for myself. And that's one of the things, like, to all the listeners on here, all the attendees, that you see that there are multiple products, and in the end, they're designed for specific reasons, for specific types of communication. And Robbie, for example, is an excellent communicator and was able to describe these products very clearly and succinctly. But in the end, you know, your local offices in the Hurricane Center are the ones that you want to go to figure out basically what you need to prepare for. Because
Ron,
we're never going to get it. I'm sorry, go ahead.
And I'll add that, remember, this is a high level product, and that really it's you guys, the Charleston office, that then downscale it to the more intricate, locations. So I think we have to keep that in mind, that the large scale products that come from the Hurricane Center may not always meet your needs, and that's where they need to come to you to get those more specific decision support data that can help them make their decisions.
Yep, excellent point. Thanks again, Robbie. I appreciate it.
Yeah, no problem.
All right, anybody else? We're a little bit late here, but if there's any questions, speak up for Robbie. Okay, great. Thank you. Thanks again, Robbie. And if anyone thinks of anything, feel free to ask us, and we can certainly talk to Robbie and get that answered for you. So what we'll do is, we're running a few minutes behind, but we can take a few minute break here, and we're going to get back. Let's do a break until about 10:15, and then we'll come back and get started up again on the coastal flood portion.
Hey, Bob, are you still there?
Yeah, I'm here.
Hey, I just want to let you know that the product and service update is posted at the top of the NHC page.
Oh, cool. Yeah, I'll take a look at that. Thanks.
Okay, yeah, no problem.
I might have to just update my little presentation, but yeah, was there anything I missed? I forgot to really. Is the cone smaller and all that?
It's a little bit smaller. I think the most it shrunk was like by 6% at one of the times, but it's all kind of within the noise.
Okay. Excellent.
But there's nothing real significant. Like I told you, I think the experimental product, storm surge, is a little bit different because it has the colors now. And the tropical weather outlook is going to have some of those regional identifiers in the text.
Okay. Cool. Well, enjoy the rest of your day. Are you going to be signing off?
Yeah, I'll probably hang on for a little bit, and then I'm going to have to go.
Okay. All right, cool. Thanks. We can catch up later, but appreciate you stopping by.
No, appreciate it. Thanks.
All right. All right, Blair, you ready?
Yeah, can you hear me?
Yeah, and just a few seconds here, we'll get started. I don't see your webcam. If you want to have that open, it's up to you.
I'll probably leave it off during the presentation, just in the for internet purposes.
Yeah. Okay. All right, everybody. Welcome back. I got 10:15, so we'll go ahead and start back up. The next section, hopefully you had some coffee, did some push-ups, got the blood flowing again. We're going to dive into keep on the water topic, but a little slightly different discussion now. Blair Holloway, our lead meteorologist and coastal flood program manager, is going to talk to us about coastal flood program updates, and then we'll have some other related partner presentations. So hopefully you can hang in there, get to around noon, and hopefully have maybe a little time for discussion at the end. So Blair, I think you're good to go.
All right, and you can still hear me okay?
Yep, and see the screen? Yep, so you should be good.
Perfect. All right. Like Bob said, I'm Blair Holloway, and I'm one of our lead forecasters here at the office in Charleston. And I'm in the, just for internet purposes, I'm going to leave my camera off here. Hopefully that will make things run a little smoother. And I'm going to go through just a few updates regarding our coastal flood program. Let's see. All right, just a brief outline. Go through kind of an overview of the coastal flood program. Although I now see that it says coastal food program. That's nice. We'll first touch on a review of the 2021 coastal flood season. Go through the watch warning advisory products and total water level forecast, and then a couple of additional things to touch on, including the AHAPS transition, and then some upcoming updates for the National Ocean Service title datums. All right. First thing I wanted to go over is just a broad overview of our coastal flood program. Our program really revolves around our two National Ocean Service tide gauges that we have along our coast. One is in Charleston Harbor, and we have continuous data there that goes back to 1921. And just as a reminder, we've determined over the years that minor flooding begins there when the tide hits 7 feet above mean lower low water. Moderate flooding begins at 7.5 feet above mean lower low water, and then major flooding begins around 8 feet above mean lower low water. So those are the thresholds that we're working with. And at Fort Pulaski is our other gauge down there at the mouth of the Savannah River. We have continuous data that goes back to 1935. Minor flood stage is there at 9.5 feet, moderate flood stage at 10, and major flood stage at 10.5 feet. And our responsibility is essentially to issue coastal flood watches, warnings, and advisories for the entire coast, and we use those two tide gauges to do that. So first, we'll look back at the 2021 coastal flood year at Charleston Harbor first. So we had 46 tides that reached or exceeded 7 feet mean lower low water, and that ties for the fifth most that we've had on record, and we now have 100 complete years of data. We had eight tides that reached or exceeded 7.5 feet, or the moderate flood stage, and that ties for the eighth most on record. And then we had 4 tides that reached or exceeded 8 feet, which is now tied for the third most that we've seen in any given year. And to dive a little deeper into that, November was particularly busy. We actually had 3 of the top 15 tides on record that occurred in the month of November, the highest of which occurred on November 7th, when the tide peaked at 8.51 feet. And that now ranks as the 10th highest on record, and is the 5th highest non-tropical tide on record. So pretty significant tide even to occur outside of a tropical system And just a few other notes. We've had 40 tides of 8 feet or higher on record, and about 65% of these have occurred just since 2015, so just in the last 7 years. And we've had 32 non-tropical tides of 8 feet or higher on record, and 75% of these have occurred since 2015. So pretty significant uptick, really at all 3 different levels here, just especially in the last 5 to 10 years. So taking a look at the same data for Fort Pulaski, we had 7 tides of 9.5 feet or higher, which is the sixth most on record. And we had 3 of 10 feet or higher, which is tied for the most on record for any given year. Of those 3, 2 actually now rank in the top 11 on record for any tide. And again, this is all part of the busy November that we had. And similarly, on November 7th, the tide reached 10.45 feet, and that now ranks as the 4th highest tide on record, and is now the highest non-tropical tide that we've seen recorded there for Pulaski. Kind of a similar story, 21 tides of 10 feet or higher, and 2/3 of these have occurred just since 2015. And looking at the non-tropical tide events, about 75% of those above 10 feet have occurred since 2015. So again, very similar story with a significant increase in the last few years. And I'll just briefly mention that the 10.5 foot or the major flood level, no events in 2021, and only 3 on record, actually. All of those are associated with tropical events. So we had the unnamed hurricane from 1947, and then the top 2 on record, which is Matthew from 2016, and then Irma from 2017. And I'll just briefly mention, if you're interested in more kind of statistics and graphs like these, you can visit the Coastal Flood Event Database at the link there below, and find more data like that. All right, so to continue our overview of the program, I'm going to go over the different coastal flood products that we issue. And the first one I'll mention is the Coastal Flood Watch. So this is issued when we expect major coastal flooding to occur within the next 12 to 48 hours. And as a reminder, the major flood level at Charleston is 8 feet, and the major flood level at Fort Pulaski is 10.5. So if we're expecting the tide to reach or exceed those thresholds at that kind of time range, we will issue a Coastal Flood Watch. Next product is the Coastal Flood Warning. This is issued when major coastal flooding is expected to occur within the next 12 hours. And so oftentimes the Coastal Flood Warning will be preceded by a Coastal Flood Watch, but not always. There might be times where leading up to it, we're not anticipating it's going to reach that major flood stage. But then once we kind of get in within the 12-hour time period, it looks like it's going to, and that we'll issue a warning without having a watch in effect beforehand. And the product that you'll see more frequently is the Coastal Flood Advisory, and that's issued when we expect minor to moderate coastal flooding within the next 12 hours. So that's anything above 7 feet mean lower low water at Charleston, and anything above 9.5 feet for Fort Pulaski. These watch warning advisory decisions are based on what we call a total water level forecast. And you can see on the hydrograph there to the right, that total water level forecast is essentially just a tide forecast. This is something that we do in-house. So that right-hand side of the graph there shows you what we're forecasting out over the next 3 days. And you can see the different, for the different high tide and low tide values. These forecasts are created at a minimum twice per day, and then we always update them in advance of a flooding tide. So we try to refine the forecast as we get closer in time, and we'll update that forecast more frequently. So these tide forecasts are what we're using to make our watch warning advisory decisions. Next thing I'll touch on is kind of how we group the counties together when we issue these products. And so we are always going to put certain counties or forecast zones in a group together for consistency's sake. And we've determined over time, that these are the areas that kind of roughly tie together to a particular tide gauge. So the first one I'll mention is the Charleston Harbor tide gauge group, and this will always be all of Charleston County and the coastal portion of Colleton County, so essentially the Edisto Beach area. So anytime we issue a watch, a warning, or an advisory, a coastal flood watch, warning, or advisory, we will always have those two counties together, and they will be based on the Charleston Harbor forecast. The one exception I'll mention is what we call tidal Berkeley County, which is basically the Daniel Island area around Charleston. If we are forecasting a tide at Charleston of 8 feet or higher, that portion of Berkeley County will get a coastal flood advisory. And in the exceedingly rare case where we have a forecasted tide of 9 feet or higher at Charleston, we will include that portion of Berkeley County as a coastal flood warning. So those aren't quite as common, but just wanted to mention that as well. So down at Fort Pulaski, it covers the rest of our coast. So these are the counties that we've tied together based on the Fort Pulaski forecast that we produce. And this includes Beaufort County, as well as coastal portions of Jasper, Chatham, Bryan, Liberty, and McIntosh counties, all the way down to basically our entire portion of our Georgia coastline. So you will always see these counties grouped together for these particular coastal flood products. And we've already talked about kind of flooding and inundation with regards to tropical events, and just wanted to mention that the forecast and the observations you see for those two tide gauges will always be in mean lower low water, but it's a little different obviously with how we handle and communicate tropical events. So during those you will see a reference to inundation, and that's water above ground level, as well as this mean higher high water, or MHHW. During a tropical event, we will still be creating our total water level forecasts, but it's important to remember that's a deterministic forecast for one very specific point. And as we've seen, we talked about with the Gracie example, it might not be where the peak surge is observed. So things get a little more complex when we're talking about tropical events. So these forecasts will still be created, but it's hard to make kind of, I guess, broad conclusions over a larger area just based on that one forecast for the one tide site. And also, if we're anticipating that 3 feet of inundation, you will see storm surge watches and warnings. And so it won't be these coastal flood products, but we could have, if only a portion of our coastline is included in a storm surge watch or warning, we could still have a coastal flood advisory up against it. So you could see those two different products kind of up against each other. All right, so that's kind of the overview of the coastal flood program itself. A couple other things I wanted to mention while we had everybody together, and this isn't necessarily specific to coastal flooding, but it's also to any hydro data and forecasts that the Weather Service produces. You're likely familiar with our AHAPS, which is the Advanced Hydrologic Prediction Service. I'm sure you've seen the webpage and you've seen these hydrographs before over the years. And we just wanted to mention that this system is eventually going to be replaced and will evolve into this, what's being called the National Water Prediction Service, or NWPS is the acronym there. The underlying data between the two will essentially be the same, but the look and feel is going to really be a lot different. And you can see on the right-hand side there, what the kind of the traditional hydrograph that we've been working with for many years now, and what that's going to look like under this new NWPS system. There's quite a few improvements and enhancements that are planned with this NWPS transition. Number one, it's going to be a mobile-friendly interface, so it'll be something that'll be much easier to pull up on a tablet or a smartphone. You've probably heard to some degree about the National Water Model. Right now, that data is kind of hard to access. but that's going to be integrated directly into the NWPS system. So that data will become much more visible and something that you can deal with on a much easier basis. Lots of improvements to base maps, and you can view different spatial layers, other NWS hazards, like I said, national water model data, precipitation data. You're going to have, as a user, you're going to have more control over the actual hydrograph as well. As it stands right now, the hydrographs are only generated or updated every 15 minutes. That's going to go away under the new NWPS system. You'll be able to control kind of the time period that you're looking at on the hydrograph itself, so it gives the user more control. There's more observational data stored that'll increase from 10 to 30 days, so you can look over a longer time period. And you can view the official National Weather Service forecast for river points or for tide gauges, and then you'll have a separate hydrograph view where you can actually view National Water Model output as well. Right now, the rollout timeline, at some point either this month or in June, there's going to be a 30-day test where AHAPS and NWPS will be running in parallel. And then later this year, September, October timeframe, there's going to be a plan to be a 30-day stability test for the NWPS, and with the idea that hopefully by late October, NWPS will be going live and become operational. Of course, those timelines are subject to change, and any updates to that, I'll be sure to send around and keep everybody updated. All right, the last thing I wanted to touch on before taking any questions is I just wanted to mention that we're coming up on an update from the National Ocean Service regarding these tidal datums, and we've talked about these today with the previous presentations as well. And just a reminder, a datum is essentially anything that you're measuring something against. So in this case, we're measuring water levels. The NOS establishes what they call these tidal datums, and we're familiar with a lot of the terminology, mean high water, mean sea level, all the way down to mean low water. These tidal datums are calculated based on what is called the National Tidal Datum Epoch, and that's a 19-year period of observations. The current epoch that we are working from includes observations from 1983 to 2001. So that's what we've been working on. That's what our basis of these tidal datums has been now for a number of years. And prior to that, the previous tidal epoch was from 1960 to 1978. The new tidal epoch that's currently being calculated covers the time period from 2002 to 2020. And although it's out in the future, these new tidal datums are not scheduled to be released until the year 2025, so we still have a few years. It's always good to go ahead and introduce this just so it's something that we can be thinking about. And I guess the main question is, why does this matter? Why do we care about this? And you can see the link that I have here underneath the graphic, the epoch update page. If you're interested, they've got a lot more graphics and different things, like a frequently asked questions page. You can visit that and get more information as well. But I wanted to go through an example and try to bring attention to why this change in the tidal datums is going to matter. And I'm going to go through an example here, and I'm using kind of a hypothetical example from Fort Pulaski. So let's consider that we have a water level of some height. So we can see that there on the graphic. And like I mentioned before, right now we are working on the tidal datums based on the 1983 to 2001 time period. So that level that we put here on the graphic is what we're considering mean low or low water based on that epoch. And so we know against that version of mean low or low water, let's just say that we're looking at a 10 feet above mean low or low water. That's the water level that we're looking at here on the example. So what I wanted to do is, let's think about this in context of the previous tidal datum epoch that I mentioned from 1960 to 1978. And like I said, these get recalculated every 19 years. So we know that the previous epoch, the datums there were 1/4 of a foot lower than they are in the current one that we've been working with. So from the previous epoch, the mean lower low water level is 1/4 of a foot lower. So even though the water level itself that we're considering here has not changed, we're getting a different observational value. So this exact same water level using the previous calculated version of mean lower low water is actually 10.25 feet. Whereas today in the current tidal datum epoch that we're working with, this exact same water level is just 10 feet. So let's think about this now using a calculation or kind of a hypothetical of what the new epoch is going to be. So let's say, and we're just going to hypothetically say it's going to be 1/4 of a foot higher than the one that we're working off of now. So that means that our new calculated version of mean lower low water in this example is 1/4 of a foot higher than the one that we're working from now. So again, the exact same water level, you look at 3 different tidal datum epochs and you get 3 different observational values. So at Fort Pulaski, under this, we're assuming 1/4 of a foot rise. That means that the exact same water level today of 10 feet is actually going to be 9.75 feet under the new epoch. So kind of a hard thing to explain, and it can be confusing because you're looking at the same water level, but you're getting 3 different heights depending on the tidal epoch that you're using for the datum. So with this transition coming in the next few years, there's a few things a few issues or potential issues to consider. Obviously a communication concern, because when the NOS flips that switch, what people think of now as a 10-foot tide or a 7-foot tide, they have a good kind of mental picture of what that means. Well, now the observed value that we're going to be getting from the tide gauge is going to be different. So a 7-foot tide today under the new data is actually going to be, let's just say, 6.75 feet or something different. This likely will require altering the thresholds that we've set for minor, moderate, and major flood categories at Charleston Harbor and Fort Pulaski. So there's going to be a communication, a change there. Those have been really hammered home, in the heads of the public for really the last probably 15 to 20 years. And datums are a challenging thing and aren't particularly well understood anyway. So I think tidal datums are even more so because they change over time, as we've seen, depending on the time period that you consider. So the kind of the question for us here is, how do we communicate this change to the public? And I'm hoping that the Ocean Service will come out with some really good material that will make that transition a little easier to communicate and understand. And I'll just, again, this is just an example. We don't know exactly what the changes in the datums are going to be for the upcoming update, but this is just a hypothetical example. All right, that is all that I have for things to update on. At this time, I'll open it up and see if there are any questions.
Blair, I have a question. For some reason, my camera's not turning on. Let's see. There it is. Is there time for a question?
Yeah, I think so.
Okay. So as one who is a science teacher educator working with middle and high school teachers who have very little background in any of this, I just want to make sure that between the last 2 sessions that I heard the right thing. So it sounds like you're measuring coastal flooding against mean low water, but the storm surge is measured at a 0 of mean high water. Did I hear that correctly?
Yeah, so we use the mean low water for really the majority of the year. The change or the reference to mean high water during tropical events is because when we're looking at storm surge inundation, that inundation is being put in the context of above ground level. And the
Correct.
closest thing we have to a, referring to a ground level is using mean higher high water. That's
Right.
the tidal datum world. That's our closest thing to the ground level. And so when we refer to it during a tropical event, that's going to give you the closest kind of apples to apples of comparison, thinking about inundation above ground level, and then comparing it to a specific, observation using the mean higher high water datum is going to provide the closest thing to a direct comparison.
Well, that makes perfect sense. But when you're talking with a high school student about sea level rise, and then let's come back to what you do in coastal flooding. And instead of talking about a 7-foot tide, you're now saying that a 6-foot something is the exact same thing. And then they'll say, but I thought you said sea level was rising. So that you have correct. This is going to present some literacy and communication things here. I can imagine why would the baseline just not have stayed the same, and you say it's now 10.25 instead of 9 point something?
Yeah, I mean, that's just the nature of tidal datums and how they are, how they're calculated. You could switch it and compare or base your observations on a different datum like NAVD 88 or something like that doesn't necessarily change.
Right.
That's just how the Ocean Service presents its data and calculates the underlying datums.
Okay, well I want to just do the best job I can to communicate the right information. So thanks for that. Awesome.
Sure. All right, any other questions? I'm not hearing any, and I don't see any in the chat. So with that in mind, we'll go ahead and move on to our next presentation. Let me see here. All right, Lori, I am going to share with you. While that goes through, I'll go ahead and introduce Lori. So our next speaker is Lori Hogan, and she is the acting chief of the Hydrologic Services Division at Eastern Region Headquarters in the National Weather Service. And she is going to introduce us to coastal flood threshold maps.
You might have to unmute yourself, Lori. Are you talking now?
Hey, Lori, can you hear us? Oh, Bob, it says that she's muted by the organizer. Let me see.
I'll unmute again just to make sure. Are you there?
Yeah,
Lori?
sorry about.
Oh, there you
Yeah, can you guys hear me now?
Yeah, sorry about that if it was
Yeah.
on our end.
Yeah, sorry about that. Hang on, I'll get my presentation back up. Okay, hopefully.
All right, we're good.
Okay. So, good morning, everybody. It is really my great pleasure to be here today. My name's Lori Hogan. I work up at Eastern Region Headquarters of the Weather Service. My position here is Hydrologic Services Program Lead. I also work and support the local offices in their total water level forecast program. My particular talk today is a new service that we're working on providing out to the public. The title is Experimental Potential Coastal Flood Extent Mapping for Effective Decision Making. The partners in this effort are the NOAA Ocean Office of Coastal Management, particularly Doug Marcy and Matt Pendleton down at that office, and then myself. And I'm going to step forward with my slides here. Before we jump into that particular product, I wanted to highlight our Eastern Region Coastal Flood webpage. Blair had mentioned the AHAPS pages. In the last 2 years, we've developed a coastal flood web page. If you go to the Charleston WFO office, under their main map on the page, there's a little icon there and it'll say coastal flood. And that will get you over to this URL. As we've been talking, you know, the coastal flood problem is really a challenging problem. You have the you know, the water levels, but then you have the waves and the winds. So this coastal flood page is a collection of all those resources. So you'll see the hazard layers there. You can display offshore buoy information, wind and gust and wave forecast grids. And then hopefully in maybe the June timeframe, you'll also be able to see these potential coastal flood extent mapping layers. So brief introduction of the purpose of the layers. There's a lot of information that the Weather Service and NOAA provides during the tropical season. You've seen a lot of this in the talks from Bob and from Robbie. But during the extratropical season, there really hasn't been a lot of authoritative information that talks about what that water level impact, what that extent of that flood is going to be. A couple years ago, then Doug Marcy from Charleston there had reached out to me and said, hey, what if we combine some of the things we're doing with the sea level rise viewer with your Weather Service coastal flood thresholds? And then based on that collaboration, we've developed these layers. So these layers are not going to be the be all end all. They're filling a gap until we have better science available from NOAA and the National Weather Service. Additionally, when I show you these layers, be aware that the layers do not provide you a water level depth, and it is not a forecast. It's really a representation of that minor, moderate, major level, and those are a function of average storm impacts over time. So again, this is a reference layer, but it's not a forecast. So I'm going to give you just a kind of quick schematic of how we've developed the layers. And imagine you're running a line, say from a tide gauge inland. And what I'm showing you on this presentation is, and it's been talked about earlier, is this digital elevation data. So imagine this is like a mathematical description of the Earth's surface. So as you go from the ocean, and you know, here's maybe where your tide gauge is located, then you're going to go inland, right? So we have this mathematical description of the elevation. The next thing we're going to use for these layers is we're going to use these flood categories. So in this case, we're looking at the minor flood category. You can see there's a water depth between what the tide gauge is at and then this minor level. And then we're going to extend that line inland like a tabletop. Then we can go up to that moderate level. We're going to extend that line inland like a tabletop, up to the major level, extend that line inland like a tabletop. Once we do that, we're able to identify what we see as wet areas, and anything under the orange line is going to be wet. We extend for a major moderate category, anything under the red line is going to be wet. And up to major, anything under that purple line is going to show wetland. Now, if we're just looking at the minor layer, we'll see that behind some of that initial coastline, there could be other low-lying areas. And these could be areas that are further inland that could be connected with storm drains. And in our new layers, we're going to identify those as a yellow area. When we look at just the orange minor layer, all the other areas inland here are going to look dry. So hopefully that covers a little sort of schematic depiction to explain how we created these layers. So that was a schematic description at a gauge and drawing it inland. The next thing I want to do is talk about, well, what do we do in between the gauges? And so what we're doing in between the gauges is we're combining those thresholds, say between Charleston and Fort Pulaski. And say if we're in this area, say midway between, half of that minor layer and half of the minor layer from Charleston, half from Fort Pulaski is going to impact where that layer looks like it's going to be. And this is called inverse distance weighting. In the case of this point closer to Hilton Head Island, 3/4 of the weight is going to come from that Fort Pulaski gauge, and only 1/4 of the weight is going to come from that Charleston gauge. So that's how we're doing the math of these layers in between the gauges. Okay, so we did hear a lot about tropical flooding today. And on our webpage, when we display these layers, first thing when you click on them, you're going to see this big disclaimer. And what it's really going to do is it's going to tell you that for tropical and near shore or subtropical, anything supported by the Hurricane Center, you really need to make sure you're going to the www.hurricanes.gov website first. And again, they're going to be talking to you and showing you all those products that related to those storm surge flooding maps, peak storm surge forecast graphics. And these particular layers are most appropriate to use during that extratropical season or any time when we don't have a tropical scenario. Okay, so this is just an example from this past weekend where up in the Virginia Tidewater area, there was a storm, and we're predicting moderate then major flood categories in this area. When you look at our coastal flood page, you're going to see a purple dot on the map, but then below the map, you're able to turn on this area, the potential coastal flood extent maps. In this case, because we're forecasting that major level, I went ahead and clicked on that major extent map. And additionally to those major extent, we have layers of major +1, major +2, and major +3 foot extent to highlight those really, really dangerous storms when they occur. On this particular map, you'll see that area of yellow. Again, this is that area of low-lying water or connected with storm drains. And when you're displaying these layers, it's recommended that in addition to displaying, like in this case, we're very near that major category threshold, but we're in between that 7 foot and 8 foot. So we definitely should show that, click on that layer that's major +1 in this case. And if we are really worried about winds and waves coming in, you could even consider clicking on that major +2 foot extent to look for areas that could be potentially impacted by that water level. And then this is just an impact photo from that area on that day. So again, significant flooding coming into that neighborhood, and this was 3 hours to go to high tide in that neighborhood at the time the photo was taken. So what I've done here is I have a few examples where I've zoomed in. So up in the upper left, I have the Altahama River area, that major flood category. In the center, I have the minor flood category with the moderate turned on. Here's that Hilton Head area where we have the maps that show that minor category. And then here's that southeastern South Carolina coastline all the way down to Edisto Beach. This is that northeast coastline north of Charleston, and this is that northeast coastline with that moderate layer turned on and the yellow depicted in those low-lying areas. Okay, so from my level here at the region, what we're really trying to do for the general public and the emergency managers with our coastal services, we're trying to bring in as many observations onto our web pages. So as many of your very localized water levels that are out there can be looked at and observed. We've been continuing to work on forecast service improvements. The field offices are studying their local bias of the local model biases, and they're understanding when the models are getting it right, when they're getting it wrong, and they're making adjustments to that forecast to get you the best forecast. And then we're also looking and finding ways to understand the waves and winds and that additional threat they bring into that local area. Again, Blair had talked about the watches and warnings products earlier, and then this last key piece that we're trying to solve with this, and it's not the final solution, it's an initial solution, is a flood extent map, and that's really for that extratropical weather season. Couple caveats to mention again about the flood extent layers. They're using a still water elevation assumption. So you can think of that, you know, your water is just flat surface. There's no waves, no wave setup. And so that's not being accounted in these water levels. And then again, things that would change how we would show the water levels on the surface would be future construction, if there's a new levee put in, if there's subsidence of the land, if there's erosion. Those could come if we have an update of that underlying elevation model, but for right now, you know, we're using a static model, and we'd have to do an update to account for that. Okay, so I'm going to do just a quick demo on our test page, and on the test page, here's the pop-up that you're going to see, and we're going to click that off. And what I'm going to do is I'm going to go up here and select the Charleston location. One of the new things we're going to add when we roll out the layers is the option to select and display the peak forecast at a location. So I'm going to click that, and in this example, I have some other layers on that are going to go up here and turn off all those hazard layers and just leave the gauge locations and the coastal flood extent maps on. And what I'm going to do is I'm going to zoom in here in this case, and let me move this a little bit here too. So in this case, if I'm zoomed into the Savannah Tybee Island area, this is that moderate flood extent, and we can toggle that off and on. And then if we're looking, you know, Blair had talked about how some of those locations were approaching those major levels even during the extratropical season. You can zoom in and see in this area in the yellow, very, very faintly. I'm going to brighten it up just a tish. You can see some of those low-lying areas. And, you know, the thing is a lot of times when you're having a coastal flood event, it's not really just that coastal flood. You could have heavy rain and poor drainage happening in those areas even during that coastal flood event. And I am going to zoom back out and go a little bit further up here to the north and localize up in this Charleston area. And again, you know, when you have those warnings out, coastal flood warnings out from that Charleston office, and they're expecting this major flood category, you'll have a way of depicting where and how far that could go inland. And again, the display is not showing depth, it's showing area where you have the potential to be wet. And you also have that low-lying area also depicted. And with that, I am done with my formal presentation. I'd be happy to take any questions people might have.
Great. Thank you very much, Lori. Let's see. I don't see any questions in the tab right now. If anybody has a question, just ask away. You might have to unmute yourself to do so. And you may have. I'll ask something that comes to mind for me, Lori. You may have touched on this in there. When do you have an approximate time as to when you know, like the public and external users will be able to view these extent maps?
Yeah, so great question. So we've been going through what in the Weather Service is called the experimental product policy review. It's a review that new products and services go through before they're released to the public. So we've completed that review, and the approval is up at Weather Service headquarters. There's been a discussion about these particular layers, and we're optimistic that the approval is going to be coming by early June timeframe at this point now. So that's the current timeline, and you know, hopefully, you know, we'll stick to that timeline and it will not be delayed. It's really, I hate to say it, more like a bureaucratic snag right now. So hopefully we'll get past that soon.
Yeah, great. And I'll just mention that whenever these do become you know, publicly viewable, I'll be sure to send around that link and the notification to our partner lists so that folks can get in there and start looking around at them.
Yeah, and Blair, when that notification does go out, I want to just mention to people that there is a recording of the training at not this particular presentation, but we have recorded training that will be also updated on the website. So currently that coastal flood page has recorded training, but when we release these layers, we're going to update that training and then add additional training piece to cover the layers. And then there'll also be some information in the FAQ areas about this as well. So, and when we do turn layers on, down here in the lower right, we'll be looking for feedback, and you can click on the little feedback here button and give us that feedback.
Great. Thank you very much, Lori. I'll pause for just another moment to see if anybody's got a question for Lori. Otherwise, we will start moving on.
Hey, Lori, this is Ron. Could you touch on, if I missed it, I'm sorry, I had to step out for a second. On your map there's the selection for the tide cycle. Could you show people what that does and mean?
Oh, sure. Yeah, so let me go back to the Charleston display. It's a little tricky on my laptop here versus a regular computer. Okay, so up in the upper left-hand corner, what we're showing here is your high tide cycle, and today's the morning of the 11th. So this little nub is actually positioned on the morning of the 11th. If I wanted to look at the evening high tide on the 11th, I would select this little area, and then I would move along here, and I could select the high tide the morning of the 12th, the evening high tide the 12th, the morning high tide on the 13th, and so on. So again, if in one case there was a moderate or major high tide being depicted, and maybe what I'll do is I'm going to move up here. If I wanted to go directly to when that peak forecast is being displayed, I could hit this little button here, and then I could grab that peak forecast time period. If I want to switch back to going and selecting my forecast, I just go back to that and then select any time frame along this high tide cycle area. So that's a great question, Ron. Good feature on this web page.
Yeah, that's a nice tool to have in addition to everything else there. Lots of different data sets. All right. I don't see any other questions. So Lori, thank you very much for your time today.
Welcome. Yep.
Go ahead, and I'm going to switch us over to our next presenter. All right. So Russ, you should be getting that coming your way. While we get that set up, I'll go ahead and present our next speaker. And that's going to be Dr. Russ Clark. He's a senior research scientist from the Georgia Institute of Technology. And Russ is going to talk about smart sea level sensors in Chatham County, Georgia. And Russ, I got your opening slide there. And so you are free to take it away.
All right, thank you. Good morning, everybody. I really have enjoyed the presentation so far today, especially that last tool we were just looking about at the high tide forecaster. We will definitely be using that on our project team and sharing that. Very interesting stuff. I want to give an update on a project that we've been working for the last going on 4 years now here in Savannah. With myself and a whole bunch of colleagues, the leads of which are Dr. Kim Cobb at Georgia Tech, Nick Deffley with the City of Savannah Office of Sustainability, and Randall Matthews, who I think many of you probably know as the Assistant Director for the Chatham County Emergency Management Agency. What we've been our project is really inspired by one of the graphs that Blair showed earlier with the data from the tide gauge at Fort Pulaski and the difference between Hurricanes Matthew and Irma. And while Matthew was the one that showed the highest on the tide gauge, locally on the ground in Chatham County, the more severe flooding happened during Irma. And so we were motivated to try and find a way to do a better job of getting that data out into the, understanding what's happening during those events and why, and being able to forecast it better. So with that, overall, our goal is to deploy this very high level, high density set of real-time water level monitors for the purposes of emergency planning and response, and focus on these tools for emergency management to use, but also for modeling and forecasting and long-term risk assessment. And along the way, we've had great success in really some of our favorite parts of the project around educational resources, working in the schools, and this whole issue that we've talked a lot about today, which is really just understanding terminology and getting communication and awareness, and helping people understand things like when we have a storm surge in Savannah that occurs at low tide, where we have 6 or 8 feet of buffer, if you will, and the community says, oh, false alarm, we didn't really have a storm surge, helping people understand that no, 6 hours earlier or 6 hours later, or if you look back a week in the lunar tide cycle when we had a much more extreme tide, those things make a difference, and that's really important part of the messaging that we're trying to convey. We're very fortunate that as part of our project, we've received been part of a 5-year grant program for the Integrated Ocean Observing System from NOAA. This is money that was directed through Socorro, who is our immediate sponsor and coordinator. And with this, we're able to, providing funding for looking at these low-cost water level sensor programs and deploying hundreds of sensors between North Carolina, South Carolina, Georgia, and Florida. And our team is focused on those deployments here on the Georgia coast, and we'll be able to not just sustain the ones we have, but install all the way from Chatham County on the South Carolina line down to the St. Mary's River in Florida, and everywhere in between. So very, both from the purpose of sustaining what we have, but also growing the sources of the data for what we're about to talk about. So for this particular update today, I wanted to focus on the modeling team work. I'm the computer science guy. I do the sensors and the a lot of the work in actually getting them deployed and what have you. But instead, we're going to have a presentation from some of our modeling team folks working in this space. And so we're going to do a little bit of a technology gymnastics here, but we're going to go ahead and play this presentation. And then I'll take questions at the end.
Thank you for this opportunity to introduce the Smart Sea Level Sensors modality. I'm Yomin Park, and Coastal Ocean Modeler. In this presentation, our team will show how different models help coastal communities for coastal hazard assessment and coastal resilience plan. First, with high-density sea level sensors, my coastal ocean model has provided not only water level information, but also other ocean conditions, such as temperature, salinity, and ocean current. These yellow marks indicate the location of new water level sensors. Extensive sensor network is installed in this area, from coast to inland river close to the city. The gaps between the sensors are complemented by this high-resolution coastal ocean model. Here, this color map shows the model domain with methodology. The model results are validated by comparison with not only the sensor data, but also USGS and NOAA under different environments. Compared to other models, this developed model shows good result on the Georgia coast in terms of error statistical parameters, such as bias, used mean square error, and correlation coefficient. As a result, this model plays a key role in understanding past and future water levels. For example, the web-based forecast system provides water condition to public, such as current, water level, salinity, and temperature. You can also check the future evolution of the water condition anywhere by just clicking target point. Here you can see how ocean current change over the next 3 days at this location. To travel to the future, you just need to drag the time frame in left bottom into the time slot that you want. Using this system, the coastal community can better prepare for the coastal hazard. The novelty of this technology and new knowledge also recognized in this international award as top seed finalist. The historical analysis using the model is also important for better understanding of coastal hazard. In this historical analysis, I decomposed the hurricane forcing into local and remote forcing. Here, the local forcing indicates the hurricane-induced wind and air pressure, while the remote forcing means shelf-scale waves and Gulf Stream. The main findings of this research are as follows. First, I observed the rebounding water levels that last for several weeks, although there is no more hurricane direct impact. As the rebounding water level can increase up to high tide level on the Georgia coast, it is one of the driving forces to cause salinity flooding. This historical analysis revealed that this rebounding water level is mainly caused by remote forces such as Gulf Stream and large-scale ocean process, which allows our attention to the significant impact of remote forcing in extreme water level. In addition, I found that the local remote forcing can have different timing to cause peak surging, depending on the hurricane characteristic. This peak timing variability of the different hurricane forcing is connected to critical timing of coastal hazard. For example, when local and remote forcing cause peak surging at the same time, this study revealed that the hurricane-induced storm surge can increase by up to 50%. This historical analysis has enhanced our knowledge on the coastal hazard and helped coastal management plan. As a result, with a better estimate of the coastal hazard, decision makers can make evacuation or coastal protection plans properly. The novelty and significant contribution of a study are recognized by publishing a paper in one of the prestigious journals. And now, these smart technologies, such as sensor and model, are expanding to cover the entire Georgia coast, from Chatham County to Camden County, so that we can have unprecedented data in South Georgia as well. To do so, I have developed new model with upgraded features. First, you can see the domain of previous model in left figure, which covered only north part of Georgia coast. But this new model in right figure covers entire Georgia coast as well as land parts. In the bottom table, you can see the main improvements of the new model. Here, I want to mention the grid point first. The number of grid points is one of the indicators to show the computational cost, because the grid points are used for model calculation. Although the new model uses only 10% more grid points, it has much larger spatial coverage, including land, compared to previous model. Even the new model can reproduce better the geographical feature. In these figures, you can see better resolution of new model around smart level sensors. Plus, this model has dry and wet function now. So, flooding simulation in mainland and city are possible for realistic model results, as you can see in these animations. Here, you can see how wetlands are flooded and dried depending on tide types in the Chatham County in the left and in the Cannon County in the right. Lastly, the new model can reproduce the compounding flooding properly because the hydrological forcing such as precipitation and river discharge are properly incorporated in this model. As a result, this new model provides strong foundation for future and past analysis of extreme water level. The accuracy of the new model has been validated by comparison with smart level sensors. In this slide, you can see the comparison result region by region, considering different geographical features. First, this region is close to the Savannah City. Here, the red and black line in the graph indicate observation and model result respectively. Next, comparison locations are around White Marsh and Wilmington Island. Lastly, I also compared the model result with sensor at the Fort Hudson and Tybee Island. Overall, you can see that the model result show good agreement with observation in Chatham County. In Camden County or south of Georgia coast, the model results show also high accuracy of water level. With the elevated reliability and new feature, this model will play a key role in coastal hazard assessment for entire Georgia coast. Other than Georgia project, Southeast Coastal Ocean Observing Regional Association is expanding their high-density observation system for entire U.S. Southeast coast, from Florida to North Carolina. Having said that, I have developed large-scale model as well, which cover entire East Coast and Gulf of Mexico. In this model configuration, we can selectively define the resolution of the target area for high-density observation system as add-on system. Or this large-scale model can be utilized as input data for localized high-resolution model, so that the model result can provide better prediction compared to existing model. Therefore, with this large-scale model, we can have multiple options to properly operate the localized high-resolution model depending on our needs. The accuracy of the large-scale model have been also validated with observations. In this case, I used 150 tide gauges from National Oceanic and Atmospheric Administration during Hurricane Matthew event. As for the example of the comparison result, this plot shows the comparison of the water level between model and NOAA tide gauges from Florida to North Carolina. Here, I targeted Hurricane Matthew event. We can see not only the model reproduce the tidal signals well, but also they can capture the hurricane impact, such as storm surge, properly at all locations. With the high accuracy, this model provides unprecedented information for large-scale oceanic process, including interaction between hurricane and ocean current, or temperature and salinity change inside the ocean. As the large-scale ocean process are also important drivers to affect the coastal sea level, the knowledge learned from this model will give us unique opportunity to better estimate the coastal hazard and resiliency in the future. And this all information from the developed model have been utilized for another model for their own model work.
Hello, my name is Yang Jun. I'm going to talk about how we are making use of the regional scale coastal ocean model to simulate the coastal urban flood. As Hyungmin mentioned in the previous slide, the coastal ocean model provides more comprehensive coverages of water levels across the Georgia coast and major waterway. Based on this, we are focusing more on populated urban cities or towns where multiple flooding drivers such as tides, rivers, precipitation, groundwater, and even sea level rise are interacting with our human-built environment. We chose one of the most vulnerable places in Georgia to the future climate change and sea level rise, which is the city of Tybee Island. As you can see in the city map on your right, there are several roads across the salt marshes and a lot of stormwater drainage toward the shoreline. This is our coastal urban flood modeling framework. I would like to just point out that from the coastal ocean model, we are taking the time-varying water levels along the coast, rivers, and creeks as boundary conditions, and combining them with the high-resolution precipitation data to track the flooded water on the ground and even some parts below the ground. First, we have performed the simulation for a non-extreme flood event in 2012 November Parisian spring tide, which is often called king tide and expected to be more frequent due to the sea level rise. During the event, two different flooding mechanisms were observed. One was the flooding over the bank, and the other was the flooding through the stormwater drainage system. As you can see in the animation, our model can reproduce the flood event, showing the flooded water on the ground in the red circles and subsequent soil situations in the blue circles. The corresponding drainage section shows the high tidal water flowing back through the pipe and overflowing at multiple inlets. Then here is another simulation for an extreme flood event, which is Hurricane Irma in 2017. I would like you to see mainly the figure in the middle of the animation, showing the storm tidal water cycle flowing back and forth across the salt marshes and lands while interacting with the heavy rainfalls in the left figures and saturated soils in the right figure. If we zoom into the street level, our urban flood model can provide much more accessible information on the flooded depth, extent, and timing in high resolution. As you can see in these photos, at each location, the blue flooded layer from the simulations are fairly comparable with the flood footage from the local media coverages. So the coastal communities can take advantage of this flood information, such as which street or city blocks will be likely flooded by a certain flood event, or what to prepare for their evacuation and resilience planning, especially in the future climate.
All right. With that, I will stop sharing the screen and take any questions. As you can, so again, apologies that the modeling team wasn't able to be here. They're actually presenting in at a conference this week, but they I think we wanted to, it was important, we wanted to share the updates from that work, and just to emphasize this point that a very important part of the project is, so we've deployed this rich set of sensors, and we have now starting to have longer term longitudinal data sets, including incorporating storm events that we have no shortage of on the Georgia coast, and can look at that and start to use it to validate and retrain this modeling work to get that higher density view of how flooding occurs, and you know, what are the other different aspects of it. So again, thank you for letting us share today, and appreciate the opportunity.
Yeah, thanks, Russ. I'll open it up just for a minute if there are any questions. Only thing I was going to ask is, and I was going to see if anyone from SEMA is on the call. Just be curious to see maybe how you know, the emergency management community there in SEMA is using the sea level, the sensors, or the modeling data. If anybody's on that can speak to that.
I know Randall was not, normally joins, he was not able to join today. I don't know if anybody else from the group is on. There's a separate tool that we have developed. We refer to it as the SEMA portal, particularly because it's in partnership with them and is specifically you know, informed by their needs. And that in that tool, we focus on Chatham County and on the infrastructure pieces that we're monitoring. Originally, starting off with bridges, so focus on bridges and inundation around bridges and other infrastructure. So that's the there's a whole, if you will, a whole separate tools set of tools projects related to that piece of it that's ongoing.
Yeah. All right.
All right. Thanks again.
Yeah. Thank you, Russ. We'll go ahead in the interest of time and move on here. So let me a little sharing thing here, and Liz, I'm going to send that your way, and we'll go ahead and introduce you. Our next presenter is Liz Hartgee, and she's the Coastal Services Project Manager with the South Carolina Department of Health and Environmental Control. And she is going to talk about the South Carolina MyCoast program.
Hey, can you hear me?
It was a little muffled.
Okay, I can't tell which screen I'm sharing. Three monitors.
Right now, I see a screen with kind of a background of some birds on the beach there.
Okay, let me see if I can do this.
All right, yeah, it looks like see, you might want to, yeah, swap. There you go, perfect. Yeah, okay, now we got it.
That's working. All right,
Yes.
thanks. Good morning, everyone. My name is Liz Harchie. I'm a project manager at the South Carolina Department of Health and Environmental Control, Office of Ocean and Coastal Resource Management in Charleston. For those of you that are not familiar with us, we're the state agency that's responsible for implementing the South Carolina Coastal Zone Management Program. And today I'm going to talk about the South Carolina King Tides Initiative and how we engage the public and operate that program using the MyCoast South Carolina application. And just to confirm, did my screen advance?
Yep, looks good to me.
Fantastic. Okay. So the South Carolina King Tides Initiative was started around late 2013, early 2014, to document the effect that extreme tide events have on our state's beaches, coastal waterways, private property, and public infrastructure. So at that time, DHEC established a king tide threshold for the Charleston Harbor Tide Station of 6.6 feet above mean low or low water. And as we heard from Blair's presentation, there will be an update in the title datum. So we'll keep an eye on that. Thanks for the heads up, because our threshold, of course, might change. We'll have to take a close look there. But at that time, DHEC began denoting times throughout the year when water levels were predicted to reach this king tide threshold. We would denote with a crown symbol on the annual tide tables that we put together, which are based on NOAA tide predictions. So here's that water level threshold relative to other thresholds that have been established for the Charleston Harbor Tide Station. So you can see it's slightly above the action stage threshold that's set by the National Weather Service, but it's below the threshold for minor coastal flooding, which is when you might see some tidal flooding on roads, particularly around downtown or beach communities. So at the 6.6 foot mean low or low water threshold, you might not see a lot of inundation on the roads, but you might start seeing impacts to our natural resources in some areas, for instance, along the beachfront. So with the King Tides Initiative, DHEC really wanted to develop a program that would hit on a few goals, including engaging the public in coastal hazards like tidal flooding. DHEC wanted to enhance awareness of these events and help people visualize the impacts associated with them. So in early 2014, we launched MyCoast South Carolina. And MyCoast is a web and mobile-based application that houses a series of reporting tools where users can submit reports and information to document coastal events and observations like super high tides, storm damage, and marine debris. To get started, it's as simple as registering for a MyCoast account and then downloading the free app on your smartphone. And MyCoast is a national program. There are other states and regions that are using it. But in South Carolina, we have built out 4 reporting tools on the platform. So as I mentioned, in early 2014, the King Tides and Storm Witness tools were the first that were added to the platform. And I came on board at DHEC in 2015, and at that time, we began developing some marine debris tools. So in fall of 2015, we added a tool for reporting abandoned and derelict vessels. And then in the spring of 2016, we migrated our South Carolina Adopted Beach program onto this platform. But I will, of course, focus on the King Tides reporting tool today. But really, all four of our tools kind of follow the same progression in the sense that users register with MyPost, they download the app on their smartphone or mobile device, and they use the app to collect information and share that information with us. And then we can take that information, review it, analyze it, and we can share it back out in a variety of ways. So I have a series of animations here just to show how the King Tide reporting tool works. So once you're registered and you download the app on your phone and you want to submit a report, you would just launch the app and you'd be brought to this main home screen here where we're pulling in NOAA tides and currents data for the tidal station that we're closest to. So this is the Charleston Harbor Tide Station. So we're getting these water level curves that observe and predicted water levels from NOAA. You can change the station. You can move to a station where only predicted water levels are available. You can change the screen here or Fort Pulaski, each of the other stations along the coast where water level observations are being collected. We also have the link base here, kind of educational component. And then when you're ready to submit a report, you would just hit that orange button at the bottom here. And then the app will prompt you to select the type of report that you want to add. These are the four that are available in South Carolina, so you can Tide. And then the app would ask you for a photograph. So you can take a photo directly in the app, or you can select it from your library on your mobile device. And then the app will auto-populate the date and time of the photo, which you can fill in and manually adjust those if needed. There's an open text comments field at the bottom. And then you would set your location. And the app is going to drop a pin where you're reporting the King Tide. You can zoom in on this map, zoom out, and you can tap around to move that pin drop. And then you would hit submit at the bottom. And really that's the extent of the information that we are gathering from the user. So once a report is submitted, it's not immediately public. We get a notification and we can go in and take a look at everything. We can contact the reporter if there seems to be some missing information. And then once everything looks good, we mark them public and reviewable on the MyPost website. And I wanted to show you what a public King Tide report looks like. You're getting type of report at the top, the reporter, MyPost number, the general area where the report was submitted, and then a couple features. Of course, the photographs are a big component of the report. This particular report only has one photo attached, but the tool can handle multiple photos per report. You're also getting that location information here in an interactive web map. You can zoom in or out. You can change to a satellite-based map. This is showing where the report was submitted here in red and relative to the nearest tide station. This is the Charleston Harbor Tide Station. And then off to the right, you're getting the date and time of the report. This was from November of 2021, which Blair mentioned in his presentation had some super high tides at that time last year. So the tidal overview here, MyPost is pulling NOAA tide data from the nearest tide station and appending it into these MyPost reports. So in this particular instance, this photo and report were submitted 27 minutes before high tide at the Charleston Harbor Tide Station, which is 6.8 miles away from where this photo was grabbed. And then you're getting some water level information, including what it was at the time that the report was submitted, and then some predictions and observations. So high tide was predicted at 9:40. It was predicted to peak at 7:01 above the low water, and observed high tide was at 10:24, and water levels reached peak 4. It's also pulling in from NOAA tides and currents, the observed and predicted water level curves, and showing where on the tidal cycle this report was submitted. You're also getting a weather overview. So MyPost is pulling weather data from a nearby station. So you're getting things like wind speed, wind direction, temperature, rainfall over the previous 24 hours. That can give you a feel for how much of the flooding might be due to precipitation, and how much of it might just be not related to precipitation, just due to flooding. Before a predicted king tide series, we put out advanced notifications to our MyPost members. So again, these are based on NOAA tide predictions. So we have an email notification system on the MyPost platform, and the notifications look something like this. They let members know when the highest tides are expected to occur. Of course, our water levels don't always mirror those predictions, so we can tweak these emails a little bit if water levels are running higher than predictions even before the anticipated start of a king tide series, just with an asterisk at the top of the email, for example. And then after a king tide series has ended, we put together recaps that highlight observations and compare those to what was predicted in terms of water levels and the number of king tides experienced over the extent of the series. So this is a summary that was put together for the November 2021 king tides. And so the highest water level was predicted at 7.1. We saw a 0.5 tide. We anticipated or predicted 5 tides. We saw 18 that reached that threshold. And then it's pulling in the collapse water level curve from NOAA. And then all of the king tide reports with the photos would kind of cluster together with this series recap that were submitted during the extent of that series. Our app developers also built a tool that tallies the number of predicted king tides and the number of observed king tides to date. This is on the MyPost website. It auto updates regularly, pulling observed water levels directly from NOAA tides and currents for the Charleston Harbor Tide Station. So it's kind of interesting to keep an eye on these numbers throughout the year. Another cool thing that MyPost allows us to do is track engagement. So how well are we hitting on that public engagement goal? So I pulled some numbers, and in the 8 years or so that MyPost has been operational in South Carolina, we have seen over 1,800 users register and over 2,700 reports come in, and that's cumulative across all 4 of the reporting tools that we have. MyPost also provides us with a really nice platform for sharing data. So I have broadly classified here the types of data requests that we've received over the years, including who was requesting the information and what did they use it for. So we've had requests from academics, conducting research and publishing that research. We've had professors, college professors and students reach out to us. Students working on class projects, wanting to use the data. We've had some interesting thesis project requests for the data as well. Government agencies, building presentations and publications have requested use of photographs, which is great. We've also had news outlets reach out requesting photographs. This one came to mind. This is EOS, which is the news arm of the American Geophysical Union, and they were doing a study or doing a story and requested the use of the MyPost photos, which is awesome. We're always happy to share what we have. So that's really all I have. I'll leave you with one of my favorite photos that came in through MyPost. This was taken on Sullivan's Island outside Charleston. But thanks again for inviting me to speak, and I'm happy to take questions if there are any. I will also leave you with my contact information. Feel free to reach out if you have any questions. If you'd like to use the MyPost data, we're happy to share it. And we're also always looking for collaboration opportunities. So if you have any ideas, definitely contact me.
Great. Thank you very much, Liz. I can speak from personal experience that I've used the app myself, and it's just exceedingly easy to use. It's a couple. I think it's like, as a user, I think you have to do like 3 clicks and then you're done with your report. It's really easy to use, and then from kind of the operational side, us at the Weather Service, it can be a really invaluable tool. I know we're trying to solicit, coastal flooding reports from people, and specifically thinking back to the big event that we had in November of last year, we really got quite a few reports from there. And the neat thing was that we got reports from places that we don't normally get reports, which is even more valuable for us. We kind of know the typical areas that flood, so getting reports from maybe some more obscure locations is really helpful. And like you said, the interface, you really have all the information for us as far as the knowing the exact location, having the picture, and then that the info kind of putting the time of the report in context where you are in the tidal cycle is really just an excellent added layer of benefit. So it's a great tool. We've loved using it. If anybody's got any questions, I don't see any right now in the questions pane.
I had a comment question. Do you hear me?
Yes.
Hey, it's Bob. Thanks, Liz. I just wanted to mention, you may have mentioned it, but just to point out again, when you're talking about like the predicted tide, and I'm pretty sure that's just the astronomical tide and not like our actual prediction. So I don't know.
That's correct. Yes, the advanced predictions that come out are the
right.
Not including meteorological.
Right. So I don't know, just to definitely point that out, there is a difference, and then I don't know if it could be made a little more clear in the app or anything, but at least folks should know that.
Sure.
Yeah, and a potential enhancement is if there's a way for the app or the program in general to ingest our the total water level forecast that I mentioned earlier, which we are creating, trying to take into account not just the astronomical forecast, but then what the meteorological impacts are going to be. They're going to potentially drive the water level higher or lower than the astronomical predictions. I don't know. There may be some a useful I guess collaboration there to use our forecast too.
That's a fantastic idea. We were always looking for ways to kind of enhance the app. That's something that's occurred to me, hitting in on those. It's one thing to get the astronomical tides, but it's leaving out a major factor in the equation. And so figuring out how to pull that in, we haven't figured that out yet. And if you see an opportunity for doing that, we would love to talk about it some more.
Yeah, hi Liz. This is Lori. This is Lori Hogan. I spoke earlier.
Sure. Hi, Lori.
Hi. So Blair had talked on his in his talk about there's going to be an update to the AHAB's web pages, and hopefully it's towards the end of this calendar year. When that project does update those web pages, there will be a new API service that you'll be able to grab that prediction for those gauges in Fort Pulaski, Charleston, and so you'll be able to grab that predicted information very easily with an API for those 2 gauges. So that's coming within the year then.
That's awesome, and that's something our app developers can definitely work with.
All right.
Liz,
Any other?
This is Ron. Sorry for my dog barking. The presentation was excellent. I wanted to reiterate what Blair said of how useful this service, this application is to us, given that we are the agency that has to do the advisories and the warnings for coastal flooding. And Blair and I went out, and several other teams did as well, during the November flooding of last year. And one of the things I quickly realized was we just simply can't cover the ground that we need to cover. And this app proved to be way more efficient because let's say, for example, you're trying to hit the peak of the tide. Well, you can only be in one location at a time for that. Whereas this crowdsourcing method, there's people all along the coast that can take those pictures simultaneously at the peak tide, if that makes sense. So very, very useful to us. I'm glad that Bob asked the question about the predicted versus our total water forecast. That's a very important distinction. And that's why you had the big difference on your slide there of 2 predicted versus 26 verified, or 26 that actually occurred. That's because of the meteorological influence, I would assume. So thanks so much for this talk and this application. Super, super useful to us. Thanks.
Thanks. I really appreciate that feedback.
All right. If we don't have any other questions for Liz, the last thing I'll mention, and I'm not sure, who, the person to bring this to would be, or who maybe the proper counterpart in Georgia would be, but it would be great to see kind of the same MyCoast, program expand into Georgia for the Georgia coast too, so that we could, kind of get that same kind of report data set that we have in South Carolina. So I'm not sure if anybody from the state of Georgia is on, but just throwing that out there that it would be extremely useful. All right, thanks again, Liz. And we will go ahead and move on to our next speaker, which is going to be Neil. So Neil, here comes your share. And while that's getting going, I'll just mention that our next speaker is Neil Dixon, who is one of our lead forecasters here at the Weather Service office in Charleston. And Neil's going to talk about the effects of ship-induced Bernoulli wakes on the Savannah River.
All right, thank you, Blair. Just to confirm, can you hear me okay and see my title slide?
I can hear you, see you, and see your slides.
Oh, excellent. All right, well, in the sake of saving a little bit of time, I won't cover everything in my presentation, but I'll certainly cover the highlights. And again, my name is Neil Dixon, and these effects of these ship-induced Bernoulli wakes mainly affect our Fort Pulaski tide gauge, which you've heard other speakers today talk about. So we'll jump right in, and just a little bit of background about the Savannah port. This quote was taken before the pandemic, but I think it's still an accurate quote. But the Port of Savannah is the fastest growing and 4th busiest port in the entire nation. Before the pandemic, it was averaging about 36 weekly vessel calls a week, and it handles more containers than any other port on the U.S. East Coast. And on top of that, it's the 2nd busiest container exporter in the nation. So it's busier than New York, Houston, Long Beach. And you can see from this graphic that it's exporting a little over 13 million tons of cargo a year. So just a bit of a lay of the land of the Fort Pulaski tidal gauge, which is the representative tidal gauge for southeast Georgia and for portions of the southern South Carolina coast. This gauge is located on the Savannah River. Hopefully you can see my cursor, but I'm pointing at the Savannah Harbor pilots. And the terminal itself is up the river, if you're not familiar with it. So to get to the Atlantic, you have to basically just cross down the Savannah River. And the Savannah Harbor has 3 areas where the speed limit is set, and it's mainly set to limit the size of these ship wakes. So that occurs down here by the U.S. Coast Guard dock, this other liquid natural gas facility over at this bend of the river, and then another section from Old Fort Jackson all the way up to the terminal. The ship speed limits are set. The tie gauge itself is positioned on the Savannah pilot or harbor pilot's dock, and it's about 240 feet from shore. It's at a depth of 17 feet, mean lower low water. The ships pass pretty close to the tie gauge at 580 feet on average. They can, you know, depending if ships are crossing, that can be much closer to the tie gauge. And the channel itself is rather narrow at only 2,015 feet. So you may be wondering, what is a Bernoulli wake? So I looked on YouTube and I found where this freighter was on the Columbia River, and I think this is pretty similar to what we see on the Savannah River. So while this is playing, I'll kind of narrate what's going on. So this is on the Columbia River, and you're about to see a ship that's going to move into view. And just a little bit of, I guess, physics of what's going on. As a ship sits in the water, it's just displacing the same amount of water as the ship's gross tonnage. So as the ship moves, that rate of change is compensated by a kind of a surge wave right at the stern of the vessel. So what you'll see in this video pretty quickly is that these rocks in the water will gradually become exposed because the water is receding to feed into the surge wave behind the ship. So the water has to come from somewhere, and that's what makes this a Bernoulli wake, is that the water is surging around the ship to fill this surge wave behind it. So you'll see this water rather dramatically recede. And then as the ship passes, then the surge wave will come in, and it will act like a kind of like a mini tsunami. And you'll rapidly see the water begin to rise. You can see the water level on this bridge abutment. And pretty soon you'll see the water here rapidly rise, kind of surge along the shoreline, all the way up to the vantage point of this camera. So out of sake of time, I'm going to fast forward this video, and you'll see that these water surges kind of go on for some period of time, and then eventually you'll have these oscillating waves, which is basically the waves that were generated from the bow of the ship reaching the shore. So when we talk about these Bernoulli wakes, it's not really the waves that you see kind of lapping up against the shore after passage of a boat. It's mainly that surge wave that comes in right at the as the stern of the ship is passing by. All right, so we'll get into a little bit of methodology here. So to study these, I used the Fort Pulaski tie gauge and recorded both the 1 minute and the 6 minute water level data. The 6 minute data is what we actually use to observe what the tie gauge is reporting to us. So I did this for 113 ships. They not every ship's the same. You know, some are very small in size, and others are enormous. And I did that for 113 ships, basically from the fall of 2018 to the spring of 2019. So during that course of study, captured 3 of these early container vessels. They're on the small side of the scale at only 137 meters in length. There were 8 of these Rolo vessels, which are basically like floating, car garages. They're meant for transporting vehicles, and they're larger. They're about 215 meters in length, and there's 8 of those. And then you get into the regular container vessels. You have the Panamax class, which is up to 175 meters in length. So there's a fair amount of them at 31 ships. But the majority of the ships that I observed were the post-Panamax. They're up to 335 meters in length. There were 46 of these vessels. And then the very largest are the Neo-Panamax, and these are quite enormous, 136 or 366 meters in length, nearly 50 meters in width, and they sit down in the water over 15 meters. So there were 12 of these ships in the study. So this is the Costco development. I know there was a lot of fanfare when this first reached our ports in Savannah and in Charleston. So that's the largest class of ships that visits our ports. So I think this little animation is not going to play in my PowerPoint. Let me see if I can drag this down here. All right, hopefully you can see this. But there's a website that was used called this marine traffic. Oh, it's not going to play either. Okay, I'll move that back out of the way. But basically, I can use this marine traffic webpage to get a live position of the vessels. I can get a rough estimate of what their water displacement is based on their gross tonnage. Have a really good idea what their length, width, and draught are, because that's set to the dimensions of the ship class. And then can collect the speed as they're passing by the Fort Pulaski tide gauge. So with this information, was able to categorize the data by looking at the 1 minute data and the 6 minute, just taking the difference between the absolute highest value during the passage of the ship compared to the low value, just taking the difference between the two. Did that again in the 6 minute data, and then looked at because the 1 minute data was so high resolution, was able to look at what the initial water level was prior to the ship's passage, and then what the actual peak was. So here are two examples of showing the difference in the 1 minute data, which you see here on the right. You can see it's much more higher resolution. The troughs are a little bit lower, the peaks are a little bit higher. And these are the names of these vessels as they pass by. And that's what this animation was going to show is are these ships moving up and down the Savannah River. Over in the 6 minute data, because it's 6 minutes, is averaging out a lot of the information. And plus the ships could span two different 6 minute windows. So that averages out even further. So it's a little bit more muted in its impact, but you can certainly see the impacts of each ship as it passes by. So taking that information from the marine traffic website and then having the tide gauge, I was able to create some Pearson product moment correlation coefficients for both the water displacement, the length, the width, the draught. I computed a length Froude number, a basic Froude number, a blocking coefficient, and speed, just taking several different parameters and comparing them to their impact on the water levels. And in doing this, the best correlation for both the 1 minute and the 6 minute was with the length and width of the vessels, which is pretty convenient because that's basically set to the class of the ships. So we can make a nice correlation for what class of ship is going to have on the water levels as they pass by. So that really brings us to the key result. After looking at these 113 ships, the relationship was pretty clear that the larger ships resulted in greater changes in water levels. So that's the case in both the 1 minute data, the 6 minute data, and we won't spend too much time, but also on this 1 minute high versus the initial water level. So the smaller this class of ships called the early container, in the 1 minute data, that can bring a difference about 0.3 of a foot. In the 6 minute data, just below 0.2, but you get all the way up to the Neo Panamax, and it's over 0.8 of a foot. And in the 6-minute data, it's basically about a quarter of a foot. So you're looking at about, you know, what is that, 2.5 inches of water level change on average in the 6-minute data. So it's nice to kind of understand this as a forecaster, and we're doing the total water forecast. If we see these variations in the water level and can see that there's a ship passing by, then you can understand why you're seeing, you know, kind of what looks like noise in the tide gauge. So with the 6-minute data, it was less impacted by these Bernoulli wakes, and that makes sense because it's averaging out the data over a 6-minute period. But the ship wakes in a previous study was shown to last about 400 seconds, which is a little more than 6.5 minutes. So the 6-minute data is capable of observing this data. But once you get into the fine resolution, like that solitary trough that shows up, that can last about 80 seconds. So that's kind of falling more in the realm of the 1-minute data. And you can see the difference in the in these two graphs. This is the 6-minute data, where kind of the highest water level change was a little less than 0.8 of a foot. When you get into the 1-minute data, it's in excess of 1.5, maybe close to 1.8 feet. And you can see there's a fair amount of ships in the 1-minute data that was changing the water levels by either a foot or more. So being curious, it was like, well, what has this done in the past? So looking back at all of our flood records using Blair's data set at Fort Pulaski, looking all the way back to 1997 to 2018, found there was 234 historical flooding events, and that's over our previous flood stage of 9.2 feet mean lower low water in the 6-minute data. Found that out of the 234 events, 88 events, or roughly 38% of all of our flooding events, were augmented by the passage of these ships. So 88 of these events were either caused by the Bernoulli wakes themselves, or the water level itself was increased because of passage of these ships. And this included 2 of our top 10 Fort Pulaski crests. There were 20 events that were purely a direct result of ship-induced Bernoulli wakes that were causing the flooding event. And what that looks like is what we see here in March of 2002. You can see that the natural water level would have crested below our flood stage of 9.2 feet. But because there was a ship passage right at high tide, we had a Bernoulli wake that caused a crest at 9.23 feet. So officially, this is a flooding event, and it's a direct result of a Bernoulli wake. So in summary results, the correlation coefficient indicated that the ship's length and width had the greatest correlation in both the 1-minute and the 6-minute data. And the 6-minute data was less impacted by the Bernoulli wakes than the 1-minute data. And again, that's mainly from the time scale of the 2 data sets. But the big takeaway is that larger ships result in greater water level changes. And just looking at the 6-minute data, you can see it varies from around 1/10 to a little over 2/10 of a foot. So whenever we're expecting a coastal flooding event, we see that there's an incoming ship, we can expect to see there's going to be a water level change of around 2/10 of a foot in our 6-minute data. So I know I went through that pretty quickly, but that's what I have for now. And then if we have time for questions, I can take some.
Great. Thank you very much, Neil. Anybody out there have any questions for Neil? One thing I'll just throw out there, just in case these folks are out there, just curious if anyone from Chatham County or maybe Tybee Island obviously would be impacted by these. Just if anybody from either one of those 2 happen to be on, perhaps you can speak about any experience with these or any observations or impacts.
Yeah, so these are very noticeable on the Savannah River just because it's such a narrow channel. But even in the Charleston Harbor, if a ship passes pretty close to our tide gauge, we can see some minor fluctuations, but it's nothing like we see down in Fort Pulaski. So that's one other thing I would, say about these Bernoulli wakes.
Yeah, good point, Neil. All right. Last call for any questions for Neil. Otherwise, we will move to our final speaker here today. Thank you very much for sticking with us. Sorry, we're a little off time. But let me go ahead and toss it to you here,
Okay.
Mary. It should be coming your way. While that happens, our last speaker here today is going to be Dr. Mary Koster from the University of South Carolina, and she's going to talk about this Kids Teaching Flood Resilience Project, a pre-disaster hazard risk mitigation program.
All right, can you see my screen?
Yes, we got you.
Fantastic. Now, I'm keenly aware that I am the only thing that's standing between people who have been sitting in a chair since 8:30 and lunch and letting the dogs out. I will try to be as brief and to the point, but I want to begin by saying just what a privilege it is to be even in this room with you all. I am a science teacher educator for the University of South Carolina Center for Science Education. I'm a literacy and science communication specialist. I primarily work in Title I schools where our teachers have had very, very little background, if any, in the teaching of any of the things that we've talked about today. And yet, most of these things we're talking about are supposed to be part of their standards, whether you're looking at cause and effect relationships, patterns in the data, change over time. So back in, 2015 or so, was organized Charleston's first sea level rise strategy. Some of you may have actually been in that room. They filled the Charleston County Library with all kinds of people saying we really need to start paying attention to these issues of sea level rise in our coastal city. But in that room of about 300 or 400 people in the middle of the day, in the middle of the week, was not one educator and not one student. And as I sat there, I went, my goodness, we're missing an incredible opportunity because these are basic science standards in the 3rd grade, the 6th grade, the 8th grade, and the 9th grade. And so with that, I made the proposal at this meeting that if, in fact, let me see if I can get rid of my screen, got something. If, in fact, we have a call for developing clear and immediate communication to enhance public safety, if that was the main call from this, I believed that students could do that. And so what I did is I began to learn which of the schools in Charleston were actually flooding the worst. And I worked with the City of Charleston GIS specialists, and it didn't take long to find out that it was our students who lived in public housing and attended Title I schools in these public housing neighborhoods that were experiencing the most impacts of both tidal flooding and rain bond flooding. And so we reasoned that never has it been more important to basically developing messages that result in hazard risk reduction. But the question that I then ask is, how well is hazard risk messaging working? So I went to the literature, and what I found out is that basically those who spend their time thinking about this saying it's not working in a lot of cases, primarily because the relationship between risk perception, and in other words, how much danger do you think you're in, and risk reduction behavior, you're actually doing something about it. There's a giant disconnect between sort of that information and action link. This literature review by Payton and Johnson is excellent on this subject. And so therefore, I went to the University of South Carolina Center for Science Education, and I said, I propose an action research project in which we try to work with students to learn the science of what to notice, know, and do in an extreme weather event, with the result that they create messaging of their own that meets the criteria in the literature for effective community resilience development programs. And there are 4 criteria for that. The messaging should feel like it has a high degree of self-efficacy. So the person delivering the message believes that they're going to succeed in getting you to do something. The people developing the messaging and hearing the messaging should feel a degree of empowerment. There should be some individual and community-based problem-focused coping and a sense of community and commitment to action. It's very unrealistic that any of these criteria are met by giving someone a pamphlet or having a one and done kind of public information program event. I would just throw that out there, that that's not very effective. So the research claim that we set out was that in these Title I schools, in these high flood-prone areas, that potential disasters are catalyzed by knowable situational conditions or vulnerabilities that can be effectively identified and communicated by youth. These are, this is a photo of 2 of the young girls who worked with me back in the school that was situated in this housing project. And when we started this project, they had no idea where this water was coming from. And by the time we finished it, they understood how it was that adding impervious surface to a salt marsh and all kinds of other things, storm drains that don't work, they came up with about 10 reasons why their community flooded. Add that to their understanding of how to access and interpret National Hurricane Center graphics, and they were at a much higher level of resilience than when we started. So this is the formula that I ended up really embedding in the program, and this comes from a wonderful program that I've been taking. It's the EJ Strong project that's come out of the EPA with DHEC and also Omar Mohammed of Low Country Action. He does environmental justice. So anyway, this formula says you can assess your disaster risk by thinking about what is the hazard, what is the vulnerability, and what we say is that even if you can't do anything about the degree of the hazard or your situational vulnerability, you live in a housing project that floods with every king tide, you can do something about your resilience capacity. And as a student, we are specifically looking at mitigating educational vulnerability. In the interest of time, I won't switch back and forth, but I have prepared a handout that I'll share right at the end of this so I can show you that I've actually defined all of these terms for you. But educational vulnerability is the access or the results from a lack of access to or awareness of knowledge and resources that might reduce your risk of harm. So what if a science curriculum were designed to address the problems of not knowing what to notice, know, and do in an event of a hurricane, to address and admit that perhaps there is a high level of hurricane complacency in the community? Before I start with every new group, I ask them to stand up if, when they heard that school was going to be dismissed for a hurricane, they celebrated because it was a day off of school. That's a high degree of hurricane complacency. They take that back to their parents too. And then of course, the final outcomes, can these students develop effective hazard risk communication artifacts? Our question approach is a threefold. What can you notice? What can you know? And what can you do with the information? And then I set about to design a curriculum so that the students could answer these specific questions. And you'll notice a lot of it rhymes because it's a really well-known phenomenon that when you learn something with a sense of beat or rhythm, you're more likely to remember it. What are the facts so we know how to act, what to do, what to watch, where to go? How hurricane smart are we? You'll see when I get to the innovations page that anybody working in this program can take a very quick quiz to see if you're hurricane smart or you're hurricane dumb, and you can see the areas where you're weak. We go out into the field and assess the storm drains in the field. One of the biggest things we talk about is because the #1 cause of death from hurricanes is drowning from storm surge, is how many of our students don't swim. The drowning death among Black youth is about 7 times higher than that among white youth. And that can be directly traced to Jim Crow cutting off of access to public pools and beaches and access to water safety. So as we think about, even something as simple as the 3 little pigs and you imagine that the hurricane is a big bad wolf, what if you knew something about the big bad wolf or the big bad hurricane? What makes it stronger? What makes it weaker? How fast is it traveling? How much time do I have? How vulnerable is my family? What's the way out? Do I have a plan? And for every box that we can check off, we give ourselves points for increasing our resilience capacity. So you can hear and see that we use a lot of game theory in this work too. So here's a sample situation. This would be a really worst case situation in our curriculum. A hazard level 10, it would be a hurricane predicted to make landfall just south of Charleston at high tide and full moon. So students become conditioned to always know what is the phase of the moon, when are the high tides, and what direction is the wind coming from. That's just something we talk about every day. We use that the NOAA sea level rise viewer. Every single kid knows what can happen, and we start with just 5 feet of inundation. So if your home's base 4 is on the ground floor, you score yourself at a 10. Again, in interest of time, I won't take you through any of that, but it's incredibly engaging. Our strategy is to draw in energy around this work, just as a hurricane has to draw in energy. We have to get rid of shearing forces in the upper atmosphere. What if the principal doesn't want this to happen? What if they say, we're sorry, we're doing testing, you have to do this after school? Those are all kinds of things that can cause this work to flounder. But when you find a school and a principal or a church or whatever who says, yes, please, I want hurricane resilience to be part of my science curriculum, then we're talking. Then the magic starts to happen. I want to give you a sense too of just how robust and wonderful the partnership that is emerging. I have almost no funding. I have a tiny little seed grant from Sea Grant this year. I've had small grants from the South Carolina Hazard Mitigation Program, small grants from Project Impacts. We just limp along, and it's hard. So anybody that wants to sponsor our work or bring us into a grant, that would be amazing. But just get a sense of College of Charleston, City of Charleston, South Carolina Aquarium, Citadel STEM. I could not have done this without the Citadel in-kind support. I have an entire website that's dedicated to this research. So if you click on this link here, it will take you to both the theoretical and conceptual framework of the research. And then I would love, let me just see what happens here. I would love to share with you just the tiniest bit about the e-curriculum that we've now field tested in 4 high schools this year. Let's see if this comes up. Yeah. All right. So again, every single innovation we've developed is free to use, and it only takes me a few hours, maybe 4 or 5 at the most, to come into a community and train an entire group of people on how to use all these materials. So we have smart sessions, get weather smart, get National Hurricane Center smart, get storm surge smart. I am definitely going to be adding in the things that I learned today about the storm surge modeling, because that was amazing. I just loved everything that I heard today, and I can't wait to add this back in. So these are the modules. And then you imagine your own community here. So it might be a Cub Scout group, it might be a church group, it might be a neighborhood association. It's tailor-made for that place. Here's our call to action. Step up, get ready, respond. Do you know what you got to know what to notice, know, and do. So you can see this is when I taught this at the College of Charleston, we started with this photograph. What's happening in this photograph? What's in the water? What are the dangers? This is the quiz that I told you about. We created this quiz and a public service announcement with a group of eighth graders, Black and brown students from Morningside Middle. A huge outcome of this work, we hope, is that we will broaden participation among Black and brown youth who want to go into resilience careers. You don't see much diversity at all in this practice space. Again, we go back to what are the things we can find out? We can. So this word, what can I do for myself and my community? So these are all hyperlinked to what I call NOAA Smart Tools. So this Check the Weather takes you straight to the National Weather Service, and every student learns how to use that site. They can tell you the difference between a flood watch and a flood warning. And this is the part we spend the most time on in the high school curriculum. We go through every single one of these forecast graphics, and when students come in the room, they go straight to the national, this is all during hurricane season, they go straight to the National Hurricane Center, they find out what has happened, and in the first 5 minutes of class, they're expected to be able to answer certain questions about whatever storms are out there. This Play Smart part is a part of actually understanding what are the flooding hotspots in your area. Around Burke High School in Simmons Pinckney, we found that 75% of the drains did not even work. And so we reported that to the city. They also understand what it means to be in a specific flood zone. That's not something they'd ever heard of before. This storm surge part is the part that we are working the hardest on. We're trying to do some interactive modeling. And so I'd love to get back together with the experts in this room on storm surge to make sure this is right. I could not have done this without being able to reach out to people like Ron Morales and Emily McGraw and Shannon Scaff, who's at the City of Charleston, without saying, is this thing I'm doing right? Do you support the way I've represented this? Have I done a good job of communicating what you want to see happen? And then again, imagine that this were a game and you drew a set of cards. You would not want to have all 5 of these cards in your deck. So if a storm is coming, you know what these we call them the big bad 5 are. We spend an entire period or more making plans. They don't leave the classroom that day until they understand how to make a plan. Then they go home, they make a plan with their parents, and they bring it back, and that's part of their grade. And then, of course, this water safety component is ever important, and presently working on a water safety campaign with the City of Charleston Aquatics Director to make sure that we can provide free access to water safety this summer to our kids in our public housing project. So I'm about to pass out because I haven't breathed. Here's the handout that is available for download. It's also on the website. I've been thrilled to be recognized as a NOAA Weather Ready Ambassador Program of Excellence for this work. Here is this concept of educational vulnerability. I was asked to sit on the Charleston County FEMA HMP plan, and we were able to get educational vulnerability added as a multi-jurisdictional problem worthy of being funded and investigated. And again, the last thing that I will leave you with is that when I went to City of Charleston Emergency Management Director Shannon Scaff to say, what is the number one thing you're scared about? And he said he's afraid people are not going to leave, that there's going to be this huge death toll because people think they're safer than they are. Am I back in my PowerPoint again? Yes, can you see the PowerPoint?
Yes.
Can you see innovations?
Yes.
Okay, so we created a film. It's called Never Say Whatever, Especially in a Hurricane. And that deals with what happens with a group of kids, 12 years old. Some of them do the right thing, some of them don't. And we are now field testing that at fifth and sixth grade levels in Charleston County through a case study. These pictures you see here are just outtakes. Just this, you can hear, I just want you to hear the power of their voices. Let me see if that comes through. Know what to do to keep yourself alive. So when students are invited to be the vectors for resilience, they own it. It is really inspiring. I have just been overwhelmed by the level of support. Here you'll see Ron Morales, Shannon Scaff, and our dearly beloved Butch Barfield, whom we've lost, and Katie Faith Gerling, who is just an amazing floodplain manager. These community leaders are taking their times to support kids as they become vectors for hazard risk mitigation messaging. In terms of what's next, what we really would like to do is to start to train kids teaching flood resilience teams in different communities through public information programs, however you might want that to look. My contact information is in this last slide, but if you Google me, my USC bio will come up as well. So that'll do it. Does anyone have any questions? I can't
Thank
even.
you so much.
I can't even see myself right now.
Mary, this is Ron. I just want to thank you for all you've done.
Oh, hi, Ron. Thank you. This has just really been something.
Could be something I could help you with in retirement in a few years. We'll see.
All right. I'm going to hold. Can I have that in writing? Yeah. If really.
No. But my word can be as good as writing sometimes. So we'll just see.
If there's any, I can't, for some reason, I'm not able to come into the room and see any of your faces. I don't know why. But if there's anyone that wants to reach out to me to get a sense of how we might work together, or might come into the community to share this work with you, I certainly welcome that opportunity.
Yeah, thanks for participating here, Mary. I think all the science that we've shared today is important, but it kind of loses its meaning if we can't communicate it to the public. So the work you're doing is extremely important. So thanks for highlighting that today. Are there anybody got any questions specifically for before Mary, before we wrap things up here for today?
Can you give me control back, Blair?
I think so. Let's see here.
Maybe that's why I can't get back in the room. There we go.
Okay.
There we go.
Thank you, Mary, again. Appreciate that.
Of course. It was a pleasure.
Takes a big team for sure. All right. So thanks, man. Much thanks to all of our attendees and presenters. Just wanted to wrap up with a few items, a few reminders, and we will leave it open for discussion. But If you need a course certificate, you can get that in the handout section. We'll send out copies of the presentations and hopefully the recording after the webinar as soon as we can, and reminder about the survey as well. So now it's pretty much at the end of the day here. I know we're a little late, but definitely want to leave an opportunity if you guys have questions for anything that we discussed today, or even anything else weather service related. I just have a few items there for discussion, but certainly you can ask away if there's anything on your mind. And if there isn't anything right now, if you think of something, you know, my email's there and Blair's email as well. So not hearing anything or seeing anything in the chat. Hopefully y'all can hear me or speak up. Okay, so we're not hearing anything, and so we'll end it there. Thanks again, everybody, for I think it was an informative morning and early afternoon. So enjoy the rest of your day, and we'll be in touch soon to follow up on everything. So, all right, thanks everybody.
Thanks, everyone.
Thank you so much. Have a good day.
You too.